I guess we are live. Let me just check the connection and get back to you. You also please confirm if everything is working as expected in the chat window. Let me also just check and be back in just a couple of minutes. Okay. Yeah, I can hear myself. I can also see my own screen. So just please confirm if you're able to see the screen and hear my voice, right? So that's a good confirmation that things are working as expected. So can you please confirm in the chat window if everything is cool, everything is working as expected? So that, okay, so let me mute this. Okay, everything working fine. Cool. That's good to know. So let's wait for a couple of minutes for everyone to join in. Today's session is dimensionality reduction. This is a slightly lengthy section because there's a lot of topics that I wanted to cover. Everything from how do you load data, how do you use Google Colab along with Google Drive, how to perform PCA, TSD, a bunch of tasks, right? So this is going to be slightly lengthy session as compared to previous sessions. So we might overshoot by a few minutes. So everything is good. Everything is working fine. No issues. Yeah, you can see and hear. Cool. That's good. That's good to know. I also have the chat window open so that I don't have to keep toggling between this screen and this screen. I have a chat window on a different computer so that I can look at the chat window and answer a few questions. So yeah, any questions that you may have. So somebody says, can we use tsni to reduce the dimensions and use it for fitting the data? What do you mean by fitting the data? Again, you have to be very precise in machine learning when you say something, right? tsni's biggest purpose is that it's used for visualization. When you have a high dimensional data, which is d-dimensional, what tsni does is you can easily project it to 2 or 3 dimensions. It's mostly used for visualization. Of course, this low dimensional representation, if you want to build a model on top of it, if you want to build a machine learning classification model on top of it, you can do it. Nothing stops you from doing that, right? So nothing stops you from that. But the primary purpose it was designed was from a visualization standpoint and not for the task of reducing dimensions to build models on it. That was not the primary purpose. Again, every dimensional reduction has to make trade-offs. As we discussed in the course videos, the trade-off that tsni makes is it tries to ensure that the locality or all neighborhoods, right? So given any point, it tries to preserve the neighborhoods or all the points within a certain radius or within a certain distance from the given point. It tries to preserve these neighborhoods, right? Of course, it could mess up global structure, but it tries to, as much as possible, it tries to preserve the local structure. That's why it's called neighborhood embedding. Again, tsni, stochastic, we discussed that in the course videos anyway. So that's the primary purpose. Cool. Do we use tsni PCA for feature selection? Please tell me, how would you do it? So you have d-dimensional space. What does feature selection actually mean? If you have d features, feature selection basically means pick a few features, pick d dash features out of these d features such that d dash is less than d. That is the task of feature selection. While on the other hand, dimensionality reduction is given a d-dimensional space or d features, you're creating completely new features. You're creating completely new features or new space altogether, right? So you're not doing feature selection. You're not picking 2 features amongst these d features when you're doing dimensionality reduction. When you're doing feature selection, yes, you're picking few. Suppose if you have a set of d features, you're going to pick d dash such that the d dash features are a subset of d features. In the case of dimensional reduction, you're creating completely new features. So you can't use it for the specific task of feature selection as it is defined, right? Cool. Sounds good. Do we use PCA now when we have powerful autoencoders like dimensionality? Yes, good point. So that's a good question. So please don't think that a technique is useless. If your data is simple, why not use simple techniques, right? So for example, we can construct autoencoders. Again, we discussed this in our course videos when we learn about autoencoders. Autoencoders are basically a generalization of PCA. I can construct simple autoencoders that behave exactly like PCA, right? So you can think of autoencoders as a generalization of PCA. But if your data set is very simple, why not just use PCA? Why do you want to always use a complex algorithm? Again, don't, a lot of people have this fascination that we should always use the most complex algorithm that's available. I think that is a misplaced ideology and a misplaced concept. The whole of science basically says, this is called the Occam's razor, right? So based on the philosophy in science that always use the simplest model to explain your data. So if there are simpler techniques, you should prefer them because computationally they're simpler, computationally they're cheaper. You can scale this to a large number of points, while an autoencoder will be computationally expensive, of course, certainly more powerful, right? We'll do some live sessions on convolutional autoencoders in the later part of this series. But don't all, so your question is like, okay, when you have complex models, why do we need simpler models? Right? Simpler models have their own purpose. If you look at most of science, look at most of physics. If you look at undergraduate level physics, most models are fairly simple, right? Your whole of Newtonian physics is very simple mathematical models, but it's extremely powerful. Of course, it has its limitations. That's why you have other very interesting concepts like quantum mechanics and other areas, right? So at the end of the day, if a simple model works, don't just go for a complex model because it sounds cool. That's a very beginner mistake. Okay. So somebody says t-SNE only for visualization, nothing to do with model. Again, I just answered that question just a few minutes back. You can rewatch that in the live session when you replay it. Okay. Chat is showing disabled. No, I can chat. I can see the chat. I don't have it disabled. Probably there is some setting in your system maybe that you want to change, right? So it's not disabled. It's working perfectly all right. Okay. Okay, sounds good. So t-SNE only facing, only for visualization, blah, blah, blah. What is SVD solver in PCA? Good question. Again, we'll discuss that when we learn PCA. But let me quickly recap that. So how do you solve PCA? PCA basically requires eigen decomposition, right? You need to basically break your matrix into, or you need to basically obtain eigenvalues and eigenvectors, right? So that's the basic idea. Now, eigenvalues and eigenvectors. Now, how do you obtain eigenvalues and eigenvectors? There are a bunch of numerical algorithms. Remember, we learned in a couple of sessions about numerical methods or numerical algorithms, where we learned how to do integration, how to do differentiation, how to find the area under the curve. These are simple numerical algorithms. Similarly, numerical algorithms is a very large area. It's also called as numerical methods. And there are a bunch of numerical algorithms to compute eigenvalues and eigenvectors. There is a huge spectrum of algorithms. Some algorithms almost as recent as 2015. So if you want to compute PCA, if you want to do it fast, there are at least 10 major techniques that you can use to compute them, right? So the SVD solver parameter that you're talking about, basically what it gives is it lets you choose which algorithm you want to choose, right? So that's what it does. Okay, do you want to use, again, the best algorithm that I know of is basically a randomized SVD from 2015. Again, what is SVD? That's something for a different discussion because we cover that when we learn matrix factorization in our course videos, right? So that's for a different discussion. But SVD and PCA are very related to each other. Cool, sounds good. Okay, sounds good. Okay. Again, just to be clear here, we will not be able to cover every parameter that is there in a function, right? Because then we'll spend just 2 hours just going through one function. Anything that you do not know or anything that you do not understand, you should read the reference. And in most references, you also get additional reading, right? So you have to do that. There is no shortcut here. It's impossible to cover every parameter of every function because most machine learning algorithms have tons of parameters. Like for example, if I have to start explaining you how this 2015 randomized SVD works, I mean, that itself is like a 4 hours explanation on randomized algorithms, how to compute SVDs. It's fairly complex. It's not trivial. I learned it during my master's degree days, right? It's fairly complex. Cool. Sounds good. So, so let's get into the session itself. Yeah, somebody says, why do we have only RGB images? Because most colors that humans see can be represented just using RGB. That's why we use RGB colors. Okay, sounds good. So since we are short of time today and we have a very large session, I'll be focusing a lot on covering the concepts today. I might overshoot, as I just mentioned a few minutes back. We have a very lengthy session because there are a lot of topics to cover, right? So let's go step by step. Please cooperate and let's dive in. Okay, so today's session is called Dimensionality Reduction. I'm assuming you guys know the prerequisites. Okay, I've mentioned this in the announcement video also. There are a bunch of free videos in 3 chapters in our course. Again, I've listed all the chapter names. I've also listed which videos to watch from, etc. The agenda today is as follows, right? So the agenda today is we'll do code walkthroughs. The focus in this series anyway is code walkthroughs. So we'll stick to that focus. Number one, most importantly, a lot of people ignore this. How do you load actual data? Again, you guys liked the image dataset that we saw yesterday. So today also I picked up some image dataset. So I'll show you how to perform tsne and PCA on an image dataset on faces. It's a fairly large, non-trivially large dataset. So I'll show you how to actually process it, pre-process it, how to load the data. Again, I will be focusing a lot on Google Colab and Google Drive because some of you may not have the resources to run it on your own laptop. So this is again, Google Colab, the free version is very, very good. It has become stable over the last year or so. It is phenomenally good. So I'll teach you a few hacks around Google Colab and Google Drive. I'll also show you how to mount a Google Drive folder, how to load data into Google Colab from Google Drive. All of those hacks I'll teach you. In addition to that, of course, we'll do a lot of data loading. Then we'll spend some time on PCA tsne. In this session, I'll be introducing scikit-learn. This is the first time that we'll be using scikit-learn for a bunch of data pre-processing operations. And we'll also be using it for PCA tsne. Don't panic. Any new library, it's extremely simple to pick up if you have the basic foundational knowledge. I'll also show you just in one code snippet how to use OpenCV to load images. Right? So again, we are just introducing the concept. We are not diving deep into it. The core philosophy at AppliedAICourse has always been that we always try to introduce concepts as and when necessary, not teach you everything in one go. That way you know where concepts are used. Today you have scikit-learn, tomorrow you have a new library. When you have new libraries, you should evolve and start learning those stuff. Right? So there is no perfect library for any task. It changes. I've written programs before scikit existed. I've replaced some scikit code with non-scikit code. So all that happens over your career. So don't get stuck on libraries, as I mentioned earlier. Very importantly, I'll not be covering any theoretical concepts. I'll not be covering any other concepts apart from code walkthroughs here because we have covered that in the course videos. Again, the course videos also have some code walkthroughs on simple dataset, which is, if I recall correctly, it is on MNIST dataset, right? Which is very simple dataset. Today I thought I'll take a slightly more complex dataset and walk you through that. Okay, so I'll not be covering the core theory itself. Again, the key ingredients is you should know how to Google search to find out answers. So what I've done in this live session is I've tried to simulate if I was a beginner. Imagine if I was a beginner, how would I solve this problem? That I'll use Google extensively, I'll read the references. I'm assuming I have the decent basics of Python that we have covered in the previous sessions. I'll experiment a lot. Some of them will fail, some techniques will work. Lots of patience. Okay. Again, learning programming or learning new libraries requires a lot of patience and experimentation. Again, as usual, I always print the data types. I'll check what is the input, what is the output, so that I'm not making simple data type mistakes or dimensionality mistakes in NumPy arrays and things like that. Right? So first and foremost, let's look at the data. Okay, very simple data. If you just go here, you'll see the data here, which is okay. So this is a fairly decent sized data set. This data set is from University of Massachusetts, Amherst, and very good data set. Again, if you look at the data set, this data set has about 13,000. So let me highlight this. It has 13,233 images of 5,749 people, and there are 1,680 people with more than one image. Right? So if you download this, again, I've provided the download link here. I'll show you a lot of data pre-processing and data processing, the very fundamental thing where people mess up. Okay, where people do a lot of mistakes for multiple reasons. Again, you can just go to this zipped file. If you just click on this, it will download the whole thing. I think it is compressed 200 plus GB. Sorry, 200 plus MB, I'm sorry, compressed. So first thing that you have to do is download this dataset, unzip it. Again, all this you're going to do it on your computer, on your personal computer, right? Whether it's a laptop or a desktop. Okay, I'll show you how to use a few things on your computer, and then we'll move to Google Colab and Google Drive. There are a few problems in just loading everything to Google Colab. Let me tell you what are the problems step by step. So first and foremost, download the zip file. It will take a while. It's not trivial. Unzip it. All operating systems, if you just right click, you can unzip it easily. Then one thing that you can do is you can upload this whole thing. You can upload. So when you upload, right, you have how many? Look at this. When you unzip it, you get 5,749 folders. Okay, so let me just show you what it looks like when you unzip it. Okay, so just a second. So when you just unzip it, this is how it looks, right? So there is one folder for every person. Some folders just have one image. Okay, so this is the name of Aaron Eckhart. I don't know who this guy is. Okay, so so every folder contains images of that person. Okay, there are some folders with more than, I don't know who is this, Abdullah Ahmed Badawi. Okay, I think most of these are celebrities or politicians or sports stars or whatever they are, right? So there are some models and some sports personalities, etc. also. There are some celebrities. There is Angelina Jolie. I saw somewhere. Yeah, so there are a bunch of people here. So the way the data is structured is every folder contains the name of the celebrity or the person of importance, and within that there are images. This is how it looks. Now what I want to do is this. Okay, so somebody says, can we have the notebook? As always, I'll give it to you as soon as the live session is over. Don't worry about it. You will get it, just like all other sessions. Cool. So just download it, unzip it. You get all these folders. What you can do is you can just go to your Google Drive, upload this whole folder. You can just go to Google Drive, upload this whole thing into your folder. It will just create 3,500 odd folders on your Google Drive. Okay, that's one way. So what I will do is this. Okay, so what I wanted to do was I didn't want to upload every folder. Okay, I wanted to upload only some folders. Okay, so I'm just doing some filtering here. So what I've done here is this. I've taken this whole data set, downloaded, unzipped. So if you're on any Linux or Mac or any of those computers, you can just list the folders by just doing this. Okay, let me just go here. So cd lfw funneled 2. Okay, so if you just do ls here on Mac or Linux, you can do this. Again, you can do, I think, DAR in Windows if I'm not wrong. It will show you all the folders that are there. Okay, if you notice there are folders, there are also some text files. We don't want to use these text files. Again, they contain some information, but not relevant to us today. Cool. So, okay, so there are some folders like George W. Bush that have more images than others, and some of them just have few images. Again, this is the data that I just showed you from the University of Massachusetts webpage for this data set, right? So what I was thinking of is this. Instead of loading all the data, what if I only retain those folders? I only retain a few folders that have at least 100 images per person. Okay, see, there are what? There are 5,749 people, which means there are 5,749 folders. I don't want to upload all the folders. I've downloaded all of this to my computer. I want to filter. I want to apply a simple filter. Now through this filtering scheme, what I want to do is I want to just retain those folders which contain at least 100 images per folder or per person. Everything below that, I want to remove it. Okay, then I want to only upload those filtered folders. Let's assume I get some X folders now, right? Each folder corresponding to a person. I want to only upload these X folders to my Google Drive. Otherwise, it will just eat up space on my Google Drive. Okay, makes a lot of logical sense, right? Now I'll tell you why I'm choosing this 100, all of that in a few minutes, right? So, okay, somebody says we can upload and zip and unzip in Google Drive. Yes, you can do that. But the reason I'm using this methodology, one of the comments says you can upload, you can zip, you can do all of that in Google Colab. But the reason I'm doing this is to ensure that your Google Drive doesn't run out of space. And it's also easy and fast for Google Colab to read data from your Google Drive. Anyway, we are not going to use all of them. So we might as well not just process them. And sometimes processing on your computer, just like unzipping and all that, is quite fast. Okay, so one thing that I'll do first is, again, do not run this cell on your computer. Do not run this cell on Colab. Very, very importantly. This is the code that I'll run on my computer. Okay. So this is my code on my computer. Okay. So whatever is the code that I have, whatever I have is the code that I have on my computer. I've just copy pasted it. Right. So you will have to run this on your computer. Of course, change the path. This is my path. Okay. I have my downloaded folder. Again, this is Linux. Also, this is a Mac on which I work on. That's why I'm giving Mac path folders. And you all know what R is. We have covered that in the previous live sessions. It means raw string, right? So let's look at this code. I'll go step by step, and I'll also simulate as if I'm a beginner. Okay. First and foremost, how do we solve this problem? What is the problem that we want to solve? Look at this. I want to only retain those folders which have at least 100 images. Everything which has less than 100 images, I want to delete it. Everything that had more than 100 images, I want to retain it. Now think about the logic first, then we can translate into code. Translating into code is the easy part. What is the logic? The logic is fairly simple. First, I want to go into this folder, right? First, I want to go into this folder and I want to get all the subfolders in this folder. First, I want to get all the files, all the subfolders first within a folder. Now, if I don't know how to do it, it's just a Google search away. Look at, again, that's why I've even typed what Google search I have done just to make sure that you can replicate most of these. Okay, what did I do? I just said, Google, how do you do for each file in a directory in Python? And I get this result. I just took the code, read the code, understood the code, and I said, this is how you can get it. So you can use the iterators and you can say for subfolder in os.list directory. The os.list directory, if I give a directory name, look at this is my directory name, right? This single line, basically what it does is, it goes through, so it is first listing this directory. It is listing all the contents of this directory, which will give me files and also subdirectories, right? Or subfolders. It will give me all of that. Now this subfolder variable will take, in this loop, this subfolder will take one file name or subdirectory file name, which is there in this folder. Again, I'm trying to simulate as if you don't know how to do this. Just a Google search away. You Google search, you get this you get a nice tutorial, go read it up, look at what functions it's using. Look at this OS, we've already used this module earlier. There's a function called listdir, which takes a directory path, which takes a string, which should be the directory path. And what it gives is, it prints all the files and subdirectories in this, right? It's as simple as that. Okay. Now, Now once I got it, so first step is I'm trying to get all the files. Now once I got all the files, again remember that in my folder there are some files and there are some folders. There are some files also. There are some files. We have just seen this a while ago, right? So if you notice, look at this, there are some txt files also, there are some folders. So I only want to process folders. So now given each of these subfolders or each of these paths within a directory, how do I check whether it's a directory or not? Again, just Google search, is directory or file in Python? You get a nice example, just use that. Again, if you don't know, again, I've written this each line step by step so that even if you're a beginner who do not know how to do it, it's just a Google search away. As I mentioned just a while ago, you will have to Google search and be patient. Okay, you will have to Google search, you will have to read references. I'm assuming you know the basics of Python. You will have to experiment and patience, right? So there are many ways of doing it. Again, this is not the only way of doing it. This is just one of the ways of doing it. The same thing you can do it using pathlibs. There are many ways of doing the same thing. I'm just using something that is that I got when I Google searched, right? So that you can replicate the same process. Okay, so first and foremost, I got this. So what am I checking here? So this basically says, see, look at this. I'm adding my directory to subfolder, which is string addition, which means it will do string concatenation. Once I do the string concatenation, I'm checking, is this a directory? If it's a directory, only then I will go into it, or else I will not go into it, right? So in each folder, look at this. Within this, First I got the list of all the files and folders. If it is a file, I will not go into it. If it is a folder, then. If it's a folder, look at this. This whole thing is inside this. If it is a folder, then what I'll do is this. Okay. I'll check. Okay, look at this. Then if I want to know the number of files in a given folder, again, just a Google search away. Number of files in a Google folder. Got a Stack Overflow link. I experimented, tried it. It just says ost.list directory plus subfolder name, the whole path. You have to give the whole path. What it returns is basically a data structure on which you can compute length, which means you can get the number of files in that folder. So you are in this folder. There are a bunch of files and there are a bunch of subdirectories, right? So you ignored the files using this line. You went into the subdirectory. Now you said, how many files are here? If the number of files is less than 100, okay, I want to delete this directory. If the number of files here is less than 100, I want to delete this whole directory. I want to completely remove this directory. Okay, so if L is less than 100, again, just Google search delete directory in Python. Okay, some functions let you delete only if the directory is empty. Some functions like this, shuttle.rmtree, which it will let you delete even if it will delete everything. It will delete this folder. It will delete all the contents in the folder also. Else, if it is not there, if it is not so, I'll just retain it as is and I'll just print the name of the folder. Cool. Look at what I'm doing. I'm just doing a simple filtering operation here. All this code ran on my laptop. Okay, I ran this on my laptop. Very simple code, nothing fancy here. Okay, again, so when you run this, okay, let me show you. So I actually put it in my in my code editor. I use Sublime Text because it's just very simple and I like that simplicity. And when you execute it, how do you execute it? You simply go and say Python 3, right? So you just go to, you know how to execute, I hope. So you just say Python 3, Yeah, you just say Python 3 and I named this whole file as remove folders LFW. Okay, so I'm just saying execute it using Python 3 and this is the name of my Python file. The moment I run this, all the folders which have less than 100 files got deleted. Now what am I left with? Let me just show you what I'm left with. Okay, so I'm left with just this many. Remember that I did not touch the files. I just left the files as is. All the folders except these 5 folders have less than 100 images in a folder. Only these folders had it. So I'll just use this data. Okay. Again, I'm just using this 100 images because I don't want to just dump all of it into my Google Drive. Now look at the names. These are mostly Tony Blair, Colin Powell. Some of you may not know this. These are people who are very powerful around the 2001 period, right? These are George W. Bush was a president of US. Colin Powell, if I'm not wrong, was the Secretary of State. Tony Blair was the Prime Minister of UK. All of that powerful people. Donald Rumsfeld was, I think, the Defense Secretary of the US and things like that, right? So I think this data set is slightly old, but that's okay. We just have faces, right? So if I just go in here, let me go to Colin Powell. Okay, so this is one image of Colin Powell. This is another image. These are different images. If you notice, these are fairly different images taken at different times in different lighting conditions. But most of them are face images. All of them are actually face images only. Right? So cool. So this is good. Next, okay. So now I have these. So what am I left with? Okay, I'm left with these folders. Let me show you this. I'm left with these text files and these folders. Now what I do is I just upload this whole thing. When I upload it to Google, it took me a few minutes. Okay. So I uploaded a total of 1153 files that are there in the 5 folders to Google Drive. I just uploaded it. Okay. Now, of course, you can say, let me just delete all the text files and upload it. That's up to you. But I did not do that. I just uploaded all the files that I have in the 5 folders, and outside the 5 folders, I just uploaded to Google Drive. Okay. Very common mistake and very common problem that people encounter, especially when they are running Google Colab. As many of you know, Google Colab disconnects. Okay. Google Colab has this problem of disconnecting if you're not active on the Google page for long. Suppose if you want to train a large model, or if you have to wait for, let's say, 1 hour to get the results, which is not very uncommon in machine learning, right? In the real world, there are instances where I waited days to just get results. Okay, even though we had like some of the best hardware that you can get. So imagine what Google Colab does is, if you're not active on this page, it will just disconnect you. If you don't want Google Colab to disconnect you, there is a very simple hack that is given in this blog. Again, please do not misuse it. If you're not utilizing your Google Colab, it is best to disconnect it. Don't hoard. Okay, please don't hoard resources, because Google Colab, is providing all these resources free of cost. So we should respect that. And please always disconnect after your job is done. Okay, if you don't want to use it, don't keep it blocking all the time, because you're blocking someone else's constructive work. Okay, so only when you have some work which is running, some important work that is running, you can apply this methodology to avoid disconnecting. Again, I do it very, very selectively. I do it when I have to train a large deep learning model, which can take about 2 to 3 hours. Right? Otherwise, I do not apply this all the time. But if you want to do it, it's very simple. Let me show you that. But again, we will disconnect at the end of this live session. I don't want to just hoard resources. Okay, so this is a very nice blog, and the solution is very simple. Okay, you just have to copy. So what it does is, what Google does internally is, it keeps seeing if there is any activity here. If there is no activity, after a few minutes, it will simply disconnect you. Okay. Again, if somebody wants to disconnect, you can just close it. That's the simplest way to disconnect. Just close this tab, it will get disconnected in a few minutes. Okay. So if you do not want to disconnect because you're training some model, or you're loading large amount of data and you want to go get a coffee or have breakfast or lunch, whatever it is, this is the way you do it. Again, I'm using a Chrome browser just so that everybody can see it. So just right click here. There is this inspect, right? So just go to inspect. So what we are doing now in the inspect, if you go here in the inspect, there is styles, there is console here, right? So in the console, just take this snippet of code. This is JavaScript code. Just paste it here. It's very, very simple. Just paste it here. Okay, just paste it here. What this code does is, every few minutes, it will automatically create some activity. It will create a click event. Okay, so that this whole thing does not get disconnected. Okay, again, please use this very, very sparingly. Respect the free resources that Google gives us. Okay, so I just executed it. So it will keep clicking. It will keep sending an activity. After that, just close it. You're done. Right? So as soon as your model is executed, just close this window. You're done. Okay, please don't misuse it. I cannot emphasize this, because if more and more people start misusing it, Google will just disable this whole feature. Okay, use it very, very sparingly. Okay, cool. So there are many ways to terminate. So this is one way to terminate, right? So you can manage sessions and you can say terminate. Just go click on manage sessions. It will give you a window and you can say terminate there, right? So that's another way to terminate. Okay, so again, I've just ensured that even if imagine if I was doing this for the 5,000 folders, it might take more time. I might want to go get coffee or something, so that it doesn't get disconnected. Okay, very simple to follow steps. What it's literally doing is, it's written some JavaScript code so that this browser window keeps sending some event to Google Colab so that it doesn't disconnect us. Cool. Now let's go to Google Colab. Again, we are still in the data. Okay, so now what I want to do is, remember, I have already uploaded this folder to my Google Drive. Okay, I just showed you, right? I've uploaded this folder to my Google Drive. This whole data I've uploaded to my Google Drive. Now I want to connect this data which is there in my Google Drive to this notebook. Okay, how do I connect it? So there is this concept called as mounting in Linux. Remember, Google Colab internally uses a Linux box. Okay, Google Colab, to run all of your code, internally runs on a Linux box, like all major computational platforms. Or somebody says how to disconnect. Come on, just close this window, guys. I don't want to close it now and disconnect the whole thing. Okay, okay, let me show you if I can. So if I say manage sessions, it says this is the only active session. If I just click terminate, it will go. Okay, it will just terminate. I don't want to do it now, because then it will be hard for me to go through the live session. Okay, first and foremost, if I want to, so what I want to do here is this. This Google Colab is running on some computer, right? So this Google Colab is running on some computer. Now your Google Drive data, your G Drive data could be on a completely different computer. So there is some data in your G Drive that you want to connect and access it from this computer on which your Google Colab is running, right? So you do that by basically saying, I want to mount this. I want to be able to access this in some file path. That's what is called mounting in Linux. Okay, it's very simple. It's just literally 2 lines of code. Okay, first and foremost, say from google.colab import drive. Google gives you all these resources. There is a brilliant tutorial here you can follow. Okay, drive.mount. So what it says now is, so here is my Google Drive, right? Where do I want to place it in my file system? I have a file system on this computer, right? This is the computer. Again, this is a server computer on which this Google Colab is running. There is a file system associated with it. In which file path should I place this content? Virtually, actually, technically speaking. I don't want to go into Linux internals now, but where do I place it? So I'm saying, please place it in content G drive. This is the folder in which I want my whole Google Drive to be accessible from. Again, this is one folder. So when you do this, what happens is your whole Google Drive is accessible in this path on your Linux computer. Again, this Linux computer is given to you free of cost by Google. Okay. So then you have Colab, right? So one major problem that I see is this. In your Google Drive, imagine this is your Google Drive, right? Imagine if you have thousands of files in your Google Drive. In the parent, the moment you go to Google Drive, imagine there are thousands of files like this, right? Then what happens is you get an error like this. It says mount failed, or it also says the timeout happened because Google is not able to, or this box is not able to load. This box, this Linux computer which Google gave you free of cost, is not able to connect to the whole Google Drive and mount it fast because there are thousands of files here. So always organize your Google Drive that at the top level, there are only few folders. Within these folders, if you have other things, it doesn't matter. Just ensure that at the top level of your Google Drive, you don't have 1,000 files, but you have a few folders from which you want to load. Okay. Otherwise, you'll get this error. This is a very common error. Okay. So if you do not get this error, again, I maintain my Google Drive very cleanly. So I just have the few folders that I care about, and I keep deleting from my Google Drive whenever I don't need some data set. Okay. So then as soon as you do this, it gives you this instruction. It says, go to this URL in the browser. You can click on this. I'm not going to do it now. If you click on this, it will say log in with your Google credentials. Whatever is your Google ID, please log in with it. After you log in, it will give you a code. It will give you an alphanumeric code. Just copy that code and it will ask you to enter it here, then it will mount everything. It might take a few minutes, right? Very simple. Again, what are we doing here? We are connecting our Google Drive to our Google Notebook or to our Colab notebook so that I can access it. The moment you do this, this is where things get interesting. The moment you do this, if you go into this, again, this sidebar that you have, here is a table of contents, all of that stuff, right? You can also go to this folder. This basically says, so if I go here, look at this. This is my content folder. In my content folder, there is a folder called G drive. This is my G drive. If I click on G drive now, file move failed. I'm not trying to move. Okay. So in G drive, there is a folder called my drive. This is where my whole Google Drive got added here. This is my Google Drive. Okay. Within my Google Drive, I only have one folder that I'm working on right now. Every other folder I try to delete. Okay. This is the folder. And if you notice, I can go into this folder. This folder has these 5 folders with images. The rest of them, it has some text files that I do not care about. Look at this. This is the file structure. This is the file structure on the Linux box on which your Google Colab is executing. Cool. Very simple, nothing fancy. Oh, so some of you are asking, how do I get GPU resources? Again, always use GPU resources sparingly. Okay. So one thing that you can do here is this. So you have editor. Okay. Colab Pro is not available in India. You have miscellaneous site. Where is that? 1 second. So it will be there here, I think somewhere. Manage sessions. It should be easy. Oh, runtime. Yeah. So you can go to runtime. You can manage sessions. You can do, again, adding a TPU or GPU is perfectly easy. Again, if you can just go to this notebooks, it teaches you how to add GPU, all of that stuff. It's very, very simple, right? So again, we are not using a GPU today. When we do deep learning, we'll use the GPU on Google Colab also. Okay. Okay. So, yeah, somebody says latest version of Colab automatically mounts Google Drive. Yes, it does that. But I just wanted to show you the proper way to do it the first time. Again, from next time, it will automatically load this for me and all of that stuff. But there might be people who don't know how to do it. That's why I've covered this. Okay, so somebody is asking about TPUs, GPUs. Again, today we'll not be discussing about it. Let's stay focused so that we can cover the rest of the session. Okay. So next, okay. So on Google Colab, again, remember that this whole Colab is like a Jupyter notebook of sorts, which is running on a Linux box. Let's not forget that, right? So there is a Linux box somewhere on Google servers on which this Google Colab is running, and this has a file system of its own, and this is mostly a Linux box. So can I run Linux commands here? So one simple way to run Linux commands is put an exclamation and do it. So in Linux, PWD basically means present working directory. Okay, and ls basically means list the contents of this folder. Okay, I'm just running a couple of very simple Linux commands here to see, okay, what is my current directory? My current directory is content, /content. Okay, what are all the directories that are there in content, G drive, my drive? Again, in Linux, space is not taken. So wherever there is space, you have to put this backslash, not front slash. So this is all front slash. Again, Linux is slightly different from Windows. So those of you who are coming from Windows, just get used to this. Again, if you make mistake, it will throw an error. You'll quickly learn that. Right. So in this folder, which is called LFW funneled, I have all these contents right now. Cool. Now I'll run everything on Google Colab only. Okay. Now let's see how I run it. Okay. Step by step. First, what I want to do now is I want to list all the files and folders that I have. Okay. So somebody says, okay, we're going slightly off topic. I'll avoid answering some of the questions in the chat window because I'll answer whichever is relevant to the current discussion. Somebody is asking about Amazon SageMaker. That's not relevant here. You can use you can run this whole thing on your laptop also. You can use any of the cloud-based systems. Colab is free, and that's why it's so easy for everyone to use. Somebody says, what if I run out of RAM? Google gives a lot of RAM. Look at this. Google gives, okay, let me just highlight this. Okay. So Google gives 12.72 GB of RAM. Look at this. Google is giving, if I just go here, it tells me that I have 12.72 GB of RAM and 100 GB of disk. If you cannot run your program with 12 GB of RAM, there is something wrong with your code. Okay. Even the GPU resources, I think you get pretty good resources. Like I have, again, many of my teammates have trained ResNets, which are fairly complex convolution neural networks on a Google Colab GPU, the free version of it, not the pro version. Pro version is not available in India. It's available in the US for $10 a month. Okay. So if you cannot work with 12 GB of RAM, I think you have to improve your programming skills and you have to optimize your code. See, okay, it's connected due to inactivity, reconnect. Okay, that's okay. That's okay. We'll just reconnect. That's not a problem. Okay. After it crash, it will give more RAM. Anyway, so again, please don't, 12 GB of RAM is more than sufficient for most tasks that I've seen. Okay. If you are using more RAM than this, there is something wrong. There are ways to get more RAM. There are hacks around it, but I do not recommend it because it will just be misused. Okay. You have to, again, remember if at a workplace, you get like 12-13 GB of RAM box and you say, I can't run code. I mean, imagine you can't even productionize this code in the real world because who will give you 64 GB RAM, right? So please be careful when you use RAM and use it sensibly. That's all I'm suggesting. Okay, cool. So now let's do one thing. Okay. So remember that my whole data that I've uploaded is in content G drive because I have mounted my whole Google Drive here. My Google Drive is called My Drive. Within that, there is a folder called LFW funneled. Okay, I'm just creating a raw string with this. Now, what I want to do is this. Okay, so I'm just counting. Look at this code. Again, this code is run on Colab. This code is not being run on my laptop or on my computer, right? So, what am I doing here? Again, the same code that we saw earlier. For each subfolder, this is the same code that we ran on our computer, right? It's the same code. If you notice, I explained this code, right? It's the same code. I've just modified it to go through everything that is there in my Google Drive, right? So what are we doing here? For every folder in this directory, again, what is this directory? This is the directory this is the directory. In this directory, go to every folder, create this variable called P. This P is nothing but directory plus subfolder. Now I'm checking whether it's a directory or not, because as we have seen, if you recall in this structure I've shown you, G drive, my drive. Okay, in this, there are some folders and there are some text files also. So we want to ignore the text files. We only want to look at folders. So what am I saying here? Again, this is exactly the same code. I want to go through each subfolder in this directory. This directory is this. I've shown you this code, right, in the previous session. I'm just reusing that. Okay. If the path which I've constructed, which is directory plus subfolder, if it is a directory, first print it so that I get all the names of directories. Now within each of these directories, I want to list all the files. Look at this. This is my file. So this P now, P is this whole thing plus the folder name. That's what this P is. Because what is P? Directory plus subfolder. This is my directory. I'm adding or concatenating the subfolder name. And if that subfolder is a directory and not a text file or not a file, then what do I want to do? Now I want to go within that subdirectory. So within this, look at this, within this, there are some subdirectories. There are some subdirectories and there are some text files. So first I'm going through each of them. I'm ignoring all the text files here. Now within each subdirectory, I want to go to each file here. Any file that is .jpg, which means it's an image file. Any file that's a .jpg. How am I checking whether it's a .jpg? I'm just saying if the file name ends with jpg. This is just a string function. Look at this. Now I'm looking at each file that is there in this subfolder now. If the file name ends with jpg, print it and count it so that we know how many images are there. I'm just counting it. Again, we'll keep reusing this same structure again and again. So if you want to access the directory structure, the subdirectories, if you want to go through each of them, this is the standard snippet of code that you can use, right? So now when I do this, what do I get? So it prints all the folders. It prints all the images that I have. And at the end, it says there are 1140 images. Cool. So what do I have? I have a total of 1140 images across 5 folders, right? Each folder corresponding to one person. Cool. Now in these 5 folders, there are total of 1140 images, right? In each folder, there are a bunch of JPEG images. Now I want to load the JPEG image first. Now what is the way to, what is the easiest way to load JPEG images? So OpenCV is a very, very big and extremely powerful library that I've used extensively. Again, I was doing a startup a few years back, and this is prior to Amazon. And that startup, we built everything in OpenCV in C++ code, mostly C++ code, right? So I have long experience with OpenCV, almost 12, since it almost started. Okay, so what you can do here is OpenCV is one of the simplest libraries to read and process images. It's a huge library. Okay, we will revisit OpenCV wherever we need it in our course or wherever we need it in these code samples, right? Because if I start going through each of the libraries, it will not work. So first we learn the theoretical concepts and then connect it to code. So what we want to do now is I want to read an image using OpenCV. Suppose if I don't know how to do it. Okay, just simple. Read image in OpenCV Python. You get this tutorial from OpenCV itself. Okay, very simple. It's just one line code. So when I say import CV2, again, OpenCV code can be written in C++ or Python. So when you Google search for OpenCV, clearly say whether you're looking for C++ code or whether you're looking for Python code. Okay, so read image OpenCV Python. OpenCV C++ will give you C++ documentation, right? Again, OpenCV is also implemented in C++ at its core because C++ is super fast. And then there is a Python layer that is created on top of it. The Python implicitly uses and calls all the C++ functionality because C++ is super duper fast. Okay, our previous startup was about 3D reconstruction and things like that, which is super heavy computationally. Okay, sounds good. So how do I load it? Again, I've shown you, again, if you just Google search for this, if you read the documentation, I'm importing CV2. CV2 is a module name which has a function called imread. Imread is image read, right? You just have to give the path. Again, you can read the documentation here. I've shown you how to read documentation multiple times now. So just read the documentation, and this parameter is important. Okay, so let me just show you that. Okay, since we are anyway at it, let me just show you that. Okay, OpenCV Python imread reference. I don't want tutorials. I want to read the reference itself. Documentation. Okay, reference. I want to read the function reference. Okay, so where is it? Okay, I am read, where is I am read? Okay, I am read, okay. I am decode, sorry, where is I am read? I am read, yeah. So you have constant string. Again, this is the C++ syntax, because const and all are C++. Let's look at, I forgot to type Python. I typed Python, reference. Okay, anyway, I've posted it here, so I might just as well use this. So just give me a second, because I anyway have the link posted here. Okay, so this is cool. So this is the IamRead function. Instead of searching for it, we have it handy. So the IamRead, you can call it from C++ or Python. The Python syntax is this: IamRead, the file name that you want to read, and a bunch of flags. Again, you can read up about the flags. Again, there's a lot of documentation here. When the flag value equals to 0, okay, look at this. When the flag value equals to 0, it returns a grayscale image. I do not want to process color images yet. I want to keep my code simple. We'll learn how to process color images little later, not today, not in this session, right? So all I'm doing now is I'm doing CV2 to image read. So there are other ways of doing it, as somebody points in the comment section. We can read the color image and convert it into grayscale. That's one way. But why do you want to do two operations? I can just get away with one operation. This way, what it does is, when it reads itself, it reads it as a grayscale image. Okay, so my image IM is a grayscale image. We have discussed in yesterday's session, an image is basically a matrix of pixels. It's just a matrix of pixels. And since it's grayscale, for every pixel, there is a value between 0 to 255. Simple, very simple logic, nothing fancy. But I want to know what is the type of this IM. Again, remember, every time you should check what is the input parameter type, what is the output parameter type. I want to know what is the data type here. Okay, so the moment I say, okay, load the image and type, it tells me that it is ND array. Oh, now I know ND arrays. I know NumPy. I know how to process ND arrays. So it is not some new data structure. The good thing with OpenCV is it works brilliantly well with NumPy. It works beautifully well with NumPy. That's why I like it. That's why it's also very simple to use. Cool. So I say what is the type of this. I also get the shape of it. I want to see what is the size of it. What is the size of this image? So this image is a 250 cross 250 image. 250 rows and 250 columns. Now, if you want to print this image, we have seen this in the previous session, right? So how do you print it? It's very simple. Again, you can use matplotlib. You can just say just import matplotlib. Matplotlib has this function called IamShow, which means image show. Again, we have discussed this in yesterday's session also. The first thing is basically the image matrix that you want to show. And here I'm saying that I want to show the grayscale image. It's not a color image, it's a grayscale image, right? And plot.show. We've seen the same snippet in the previous session, right? So when we learned about basics of linear algebra, same snippet of code, nothing changes. So the moment, okay, I see a grayscale image. So things are looking good, right? So I've been successfully able to load one image without any hiccups. Again, I've taken Colin Powell. Many of you may not know who Colin Powell is. He was Secretary of State during the Iraq War, during the Afghanistan War, etc. Early 2000s. So this is Colin Powell. I know this. Okay, you can Google search for it. Okay, sounds good. So this is cool. Everything is looking good. Now, again, remember my data. So each image is a data point. Okay, the way I want to pose my principal component analysis. Now let's go into the problem of posing the principal component analysis problem. Till now, what we have done is basically data mangling. Okay, we basically just did a little bit of data filtering, because we said I don't want to use all the folders. So we filtered, right? And we understood the structure. Okay, we didn't do much of pre-processing also yet. Okay, all the code that we have seen till now is just simple directories, files, etc. We have also learned how to load an image into a NumPy matrix. So what do I get now? Now what I got is a 250 cross 250 matrix. It is a 250 cross 250 NumPy matrix. It's a grayscale. So the values in each pixel range between 0 to 255. Cool. This is what I have. Now the most important part, this is where theory is critical. If you don't understand the theory behind PCA, you're just doing some black box stuff. It is perfectly okay to use libraries as long as you know what is happening internally. If you just think in terms of black boxes, you will never be able to understand things internally. So the internal depth is very, very important. Otherwise you don't know what's happening. You're just going blind. Okay, so our PCA, the way we'll pose it is this. So we want each of these images. We have 1140 images, right? So we want to construct a data matrix. Okay, my data matrix will be like this. I want to construct a data matrix such that each image is a row. So image as a row. I want each image to be in one row because I want to treat each of these images as one data point. Each of these images, I want to treat them as one data point, right? Again, in the course videos also, we have done the same thing with MNS data, which is much simpler. Okay, I'm taking a slightly more complex example so that it's easier for you to follow through. Okay, so I have a 250 cross 250 matrix. I want to represent it as a row vector. Again, all this is in NumPy. This is also in NumPy. Okay, I want to take this 250 cross 250 matrix and I want to represent it as one row. Now, how do I do this? I can just reshape, right? We've discussed this in the NumPy sessions, if you recall. So I can just reshape this whole matrix and say, this is 250 cross 250. I want to represent it as 1 cross 2525 is 625, 62,500. Right? So the number of columns, or the dimensionality of data will be 62,500. The number of data points that I'll have, the number of data points n that I'll have is 1140. This is my data matrix. This is my big data matrix on which I want to do PCA and all of that stuff. Okay, first let's construct this data matrix now, step by step. That's the important part. Again, if you do not have the clarity of this, all the code is useless. Okay, that's why I asked you to already check out the theory concept so that we don't have to repeat it. So that's the idea, right? So first thing that I'll try to do is, okay, I'm saying D equals to 62,500 because I just know what is the shape of it. Now I'm trying to represent it like this. My image vector is np.reshape. We have seen this functionality when we learned about basics of NumPy, right? I'm taking an image and I'm reshaping it into 1 cross 62,500. Now when I print the shape of it, again, always check. Don't jump to conclusions. I reshaped it. I just want to check if everything is all right. Its shape is 1 cross 62,500. So what did I do now? We just created from a matrix of image, we converted into one data point, right? Cool. So now we have done it only for one image. Now I want to do it for all the 1140 images in my folders. Cool. So let's do it. So whatever I have done here, I'm just putting it into a function. Okay. Wherein I give a file name because I'll repeatedly use this, right? So I'll give a file name. It will return the image vector to me. Simple, very simple code, nothing fancy. So whatever we have just seen, I'm just putting it in a function called load image. Okay. Now let's build the whole data matrix. Okay. With each row as an image, right? So somebody says, what happens when the image has color? That's a problem because when you have an image, the ND array will look like this. Imagine if this is color image, right? So what do you get? You get something called as a tensor. You get 250 rows, 250 columns, and you get depth 3. You get depth 3 here for RGB. Again, that's an interesting part onto itself. We'll learn how to process RGB images later on, not in today's session, because that requires a good amount of time to be spent on how do we process it. There are tons of things related to it. Today I want to keep it simple. That's why I'm just operating in the space of matrices. When we learn about convolutional neural networks in deep learning, we learn about RGB images. All of that is on RGB images actually. A good chunk of it. You can do convolutional neural networks on grayscale also, but it's very easy to do it on RGB. Again, convolution that we learned when we learned linear algebra is the key idea here. Cool. So let's come back. So I want to create a data matrix. Okay, I'm calling my data matrix as data. I'm just creating a NumPy array here. I know n is 1140, d is 62,500. So I'm just creating a zeros matrix. Now I also want to store additional data. Okay, I'm creating a dictionary here. The objective of this dictionary is this. Okay, look at this. Every image at the end of the day, every image will be one row here. In addition to that, I want to store some metadata or some additional data. One metadata that I want to store here is, imagine if this is the ith row. What does this ith row correspond to? What image? What is the file name? So I want to store this. I want to store a dictionary where I want to store the row index and the corresponding file name as keys and values. So my key is the row index. I want to store this so that given any row index, I can actually load the file and see the file. Okay. So my value in my dictionary is going to be my file name, the whole file name, the full path length. I want to store this metadata so that if somebody says, okay, we are on ith row, if I want to see this image, I know where it is, right? So without worrying about it. That's one data that I want to store. The other data that I want to store is called labels. What I want to do is this. So we have what? 5 folders. We have 5 folders, each folder corresponding to one person. So all the images, so the way I'll store this is this. Suppose imagine I have 1140, look at this, I have 1140 images, right? So I want to create a simple list. I want to create a simple list from 0 to 1139 such that whatever is the first, again look at this, whatever is the 0th row, right? Whom does this belong to? Which person does this belong to? That I can learn from my folder name, right? So what I'll do is for every folder, I'll give a unique number. Because there are 5 folders, I'll use 0, 1, 2, 3, 4. For every folder, I'll use a unique number and I'll store, if the ith image comes from second folder, then I'll store that information in the labels. Again, this is very useful later on. I'll tell you why it's useful. Without this, you will not be able to visualize the data, right? Again, somebody asked, should all the images be same size? Let's ask that question, right? Imagine if images are of different sizes, okay? Then how would my data matrix look like? Okay, suppose let's assume image I has, let's say, some 10,000, let's just say assume 10,000 pixels. Image J, let's assume, has only 5,000 pixels, let's just say. Now, what will you do for the rest of the 5,000 pixels? You fill the 5,000 pixels here. Rest of the 5,000 pixels, what will you do here? You can fill zeros, NANs, whatever it is. But that's not the best way. Okay, try to keep your images all to be the same size. Again, you can resize images. If your images are of different sizes, you can resize images using OpenCV very, very easily. Again, just a Google search away, OpenCV resize images. Okay, Python, I should say Python. So yeah, again, I think more and more people are using this, right? So Python examples, OpenCV cv2.resize. Very simple code. You can just use this function called resize. It will simply resize the image for you. It's as simple as that, right? So if you want to, it's always a good habit to keep your images to be roughly of the same size so that you don't have this problem of what to fill in here, right? Generally a good idea. Cool, sounds good. So now I have this. So you understood the structure that I'm trying to follow, right? So I'm storing all of this in a data matrix and I'm storing this additional information. Cool. So let's go one step down. So I'm using this I equals to 0. I basically is whenever, the reason I'm using I and folder number is this. Look at this. This is my data matrix, right? First I'll fill 0th row, then I'll fill first row, then I'll fill second row. So ith row at any time is the one that I'm filling, right? Initially, when I start processing the folders, my folder number is -0. Every time I encounter a new folder, I'll keep incrementing this folder number. Again, this code is exactly same as previous time, but we have just changed it slightly. Look at it, it's the same structure. For every folder that is there in this, I'm creating a path. I'm checking if it is a folder. If it is a folder, I'm incrementing my folder number, right? Now for every file in this subfolder now, if the file name ends with JPJ, there are 3 things that I'm doing. First, this data matrix that I have, the ith row, whatever I get from load image. We've seen this function just a while ago, right? So what am I doing here? The ith row of this data matrix, I'm filling the contents from the image. Because load image, the file name actually gives me the row vector, right? Number 1. Next, look at this. Here I'm storing in the dictionary, I'm saying ith row corresponds to so and so file name. Look at this, this is my dictionary, right? Index file. So this says my ith row corresponds to this file name. And in my labels, I'm adding the folder number, saying that so and so at ith location in my labels list, I have the item that is there in, basically it comes from so and so folder number. Simple, cool. Simple loop. We've seen this loop two times already, right? This is the 3rd time. With this, I've created my data set. Very simple, nothing very fancy. Cool. So somebody says, minimum what size should we maintain? The rule of thumb is this. The smaller the image size, the more loss of information. Smaller implies more loss. So you can experiment with it, just don't make it too small that you can't recognize what is there. Okay, just keep it small enough so that your computer doesn't crash. And I've just kept it at 250, 250. I did not change it for the rest of the processing. Cool. Again, once I've created this, I always print and see what is happening. I always check. What is my I? My I should be 1140 because there are 1140 images. And this is my dictionary. This is my list. Always print and check. Another thing that you have to always do is sanity checks. Always make sure that things are all right. So a couple of sanity checks. First, let's look at the shape of data. 1140 by 62500. Cool. So it's working as expected. Now what I do is I take the 10th row. I take the 10th row in data and I want to see what is the max, min and mean value. Right? Because we placed the ith image in the ith row. The ith row is basically an image, which means its minimum and maximum value should be between 0 to 255. I just tested that. Okay, so max value is 255, min value is 0. I also printed the mean value just to see that it is not 0 or 255. Cool, next. Now I want to take this ith row and I want to reconstruct the image from this. Because this is my ith row, right? So what I want to do now is, this is 1 cross 62,500. Now, if I actually go back, if I reshape into 250 to 250, and if I use IM show, do I get a genuine image? Again, this is like cross-checking. This is like a thorough sanity check, just to make sure. So I take the 10th row, look at this. I'm taking the 10th row in my data, I'm reshaping it to 250, 250, storing it in temp, and I'm using matplotlib to show this image. Right? So the moment I see this image, what do I get? I get I don't know who this guy is. Okay, cool. But what is the file name here? I also want to get the file name, index file 10. What is the file name? This is the file name. Okay, this file name is Gerhard Schroeder 0069. Now I want to see this guy. Okay, this is the image. Again, on Mac, I can do it very fast. I can just type the file name and I'll get it. So this is the color image. This is the grayscale image. So whenever you're writing this complex code, where you're modifying a lot of things, always double check, triple check. Because if you have constructed your data matrix incorrectly, all the analysis you goes into the dustbin. So writing test code, this is the sanity check. And I'm doing thorough sanity check here. From the matrix, I have taken one row, the 10th row, and I've reconstructed the image, saw it, and I want to ensure that the file name that I have in the index is also sensible. Right? It's very, very important that you do these sanity checks. Cool. Sounds good. So the sanity check is done. Now, one major problem that you'll encounter, you've loaded all this data, right? Now imagine your computer gets disconnected from Google Colab. A very common problem. Okay. Let's assume suppose your browser got disconnected from Colab. So all the work you have done, you've spent a lot of time creating this data matrix, creating this index to file, right? Also creating this labels list. You've done a lot of processing to do this. Now, if your Colab dies now, all this effort is lost. So how do we avoid losing this effort? Okay, very, very important, especially when you have long running jobs, is to store this data somewhere on your Google Drive. So Python has this concept called as pickle files. What is a pickle file? Again, we discussed this in one of the case studies in our course. Those of you who don't know, it's okay. I'll just quickly explain this. We discuss in a lot more detail in our course videos in one of the case studies. So the idea here is very simple. So imagine, look at this. What is data here? If you think about it, what are all these data? What is data? Data is a Python object. Think about it. What is data here? Data is a Python object. Right, of some class. Index file is also Python object of some class. Labels is also Python object of some class. Whatever is there in memory corresponding to data, can I store it in some file? If I can store it in file as is, whatever is there in this, the binary representation of this whole thing, if I can store it in file, later on, I can read this data from the file and load it back to a variable. Now, the moment I can store it to a file, I can dump it to my Google Drive. Now, even if my browser and Colab dies, I don't have to repeat all the hard work that I've done. So a pickle file is basically a file that you can create. So pickling in Python, it's a very core foundational concept in Python. So what pickling does is, pickling enables you to take any object in Python and store it to a file. Now whatever you have stored in a file, you can also read it back. That's the cool idea, right? So what I do now is this, okay? So somebody says, can we use HDF store? There are many ways of doing it, okay? Pickling is the most popular way, okay? Somebody says, is it mandatory to store metadata? If metadata doesn't work, I'll show you what will happen. Somebody says, why did we give folder number -1? You can give any number. I gave folder number -1 because I'm incrementing it here. Look at this, look at the code, right? So as soon as I find a new first folder, the folder number becomes 0 because I want my folder numbers to be 0, 1, 2, 3, 4, right? You can give any number. If you give 0, your folder numbers will be 1, 2, 3, 4, right? So there are multiple ways of doing the same thing. There is no one right way. There are multiple right ways. Okay, so let's see how to use Google Pickle. Again, if you don't know Google Pickle, just Google search read and write pickle files. That's it. You'll get a beautiful tutorial from python.org itself. Okay, so first I create a file name. I'm creating the file name in the directory that I care about. The directory here is this directory. The directory here is my LFW funneled directory, right? So I'm saying I want to create a file name. My file name is nothing but directory plus data.pkl. Again, you need not give this extension, but many people prefer this to show that this is a pickle file. You don't have to give any extension, it will still work, right? Now, if you want to write the data object to this file name, it's very simple, pickle.dump. Again, pickle is a module which has a function called dump. You just dump this data object and you dump it by opening this file name with write references. And this is a binary file. W means write, B means binary file that you're storing. That's it. It gets stored. So I've already executed it. So that's why if you notice here, you see data.pkl file. Because I already executed this code a while ago. So I can store all this interesting, so I can store my index file, I can store my data file, I can store my labels, all of the metadata, I can store it if I choose to. Again, you can read it back from here. Suppose if you want to read the index file. For example, I dumped the index file. Now I'm reading the index file. Look at this snippet of code here. This is my index file from PKL. How do you load from PKL? Pickle.load. It's so simple. Pickle.load. Just say you want to open this file name. The file name here is directory plus index file.pickle. Read, and it's a binary file. You read it. Now if you print index file PKL and index file, they both look exactly the same. You can verify that. Right? So now if you want all of the changes that you have done to this folder, remember, very importantly, all these changes that you have done are done on your Linux box that Google gave you. Remember, as I told you earlier, right? This is the Linux box on which your Colab is running. This is the Linux box that Google Colab is running, and there is a file system in which you are storing. Now, all the changes that you have done in the file system, if you want to put it back to Google Drive, again, just because you stored the pickle file, where is it stored? The pickle storage is the whole thing is getting stored in the file system of the Linux box where you're running, right? The disk here is about 100 GB, right? There is a 100 GB disk here. This is where all the data is getting stored. Now, if you want to dump it to Google Drive, and if you want to push all of this data to Google Drive, you have to say drive.flush and unmount. So there is no single flush that I know of. So flush and unmount basically means whatever changes you have done here, flush them back to Google Drive and unmount. This will guarantee that all the changes that you have done to the local file system are written back to Google Drive. Right? Cool. So again, somebody says, so somebody asks about serialization, deserialization. Yes, pickle files implicitly, those of you who know about this, they do serialization and deserialization internally. Yes, they do it internally for you without calling them. Again, if you read how pickle files are internally implemented, it is all done through serialization, deserialization concepts. Yes, that's right. Cool. So now with that out of the way, okay, so we have our data, we have the metadata, all of that. Now I want to build PCA. Now look at this. I have, again, constructing the data is important. This is my big data matrix. What all do I have now? What all do I have? I have this big data matrix. I have this big data matrix with n rows and d columns, right? And I have index, file name. This is a dictionary which maps given any I, it basically maps I to file name, right? I also have my labels, which basically says the ith row, which folder or which person does it belong to, but the folder is represented as numbers. This is the data that I have. This too is metadata. This is the core data that I have. Now let's start working with it. Now to solve PCA, you can actually need not use scikit-learn. You can actually write it using much more simple things. For example, in NumPy, right? NumPy, you can compute, again, what is PCA at its core? You have to compute eigenvalues. In PCA, you can compute eigenvalues using this NumPy linear algebra eigen. It will give you all the eigenvalues, all the eigenvectors, all of that it will do for you. But then there is a lot more code that you have to do. Because look at this. Once you get eigenvalues, eigenvectors, there are a couple of things that you want to do, right? This is your data matrix, right? This is your data matrix. Now you want to compute your PCA. Using PCA, what do you get? You get basically top eigenvalues, eigenvectors, and then after that you want to transform this data. This is data which is d-dimensional, right? Now you want to generate another data which is n cross d dash, right? So let's assume this d dash is 50, let's just say. So this is 62,500, right? So if this d dash is 50, what do you have to do? You have to take the top 50 eigenvectors and do a bunch of transformations, multiplication, matrix multiplications. So you can implement PCA using raw NumPy, right? You can do it. I mean, you can take it as an exercise. It's easy to do. It's not rocket science. But because there is other very good libraries, again, if the library was not good, it is better for you to implement it on your own. Scikit-learn is one of the most popular, one of the most simple libraries for many, many machine learning systems. Again, it is not the best always. For example, if you want to build a specific class of models called as boosting models, right? So there is something called as gradient boosted decision trees. Scikit-learn is not the best. There is another library called XGBoost, right? Which is one of the best libraries. If you want to do deep learning, some deep learning is implemented in scikit-learn, but it's not the best library. The best libraries are TensorFlow, Keras, or PyTorch, right? So you should always pick and choose the library that works for you. For some of the basic concepts like PCA, linear regression, logistic regression, etc., scikit-learn is very, very well implemented. And the other best part here is it takes care of all of this. I can do all of this. I can just literally from this data matrix to this data matrix, I can arrive in 2 or 3 lines of code. But that does not mean that you use PCA functionality and scikit-learn as a black box. Please don't use it. You should always understand what's happening under the surface. You should have the skill to implement it on your own. Again, we have done multiple sessions, right, on basics of Python, on NumPy, SciPy. So anything that you have learned theoretically or that you have seen, that you understand the internal mathematics, most of it you can just easily implement using NumPy or Pandas. It's just a bunch of matrix operations. That's all it is. But since there is something already built, let's use it. Let's learn to use it because it will make our life simpler. And scikit-learn is fairly well implemented. There are some things which are not well implemented, but most of the things are well implemented. Again, this session we will not cover whole of scikit-learn in just one session. So good question. Somebody asks, is scikit-learn used in production? Yes. I have personally productionized scikit models. I have actually published scikit models in production. And these are like massive scale systems. Again, scikit-learn doesn't scale very well. Like it cannot use, imagine if I have 2000 node cluster. Scikit-learn doesn't work very well. If you want to do distributed machine learning on, let's say, 100 terabytes of data, then you should certainly use Spark MLlib, which is another library which runs on Spark compute platform. But for fairly reasonable systems, I have actually productionized scikit-learn in production and for some very, very important stuff. Very, very critical, very, very important stuff. My team actually did it. I wrote the scikit-learn code, put it through an API, all of that. So it works. Okay. So don't worry about it. There are a lot of companies which have put in production. It works reasonably well. Again, it has its own issues with scale and other things. If your data fits in your RAM, it works fairly well. Simple logic. Okay, cool. So again, we will not be covering whole of scikit-learn in this session. We'll go step by step and build slowly. Again, to learn any new package, today we have scikit-learn, tomorrow there will be some other package. Don't get tied to one package. The key ingredients are learn to Google search, read references, basics of Python knowledge is critical, experiment, lots of patience. I have learned some libraries which took me almost a month to become good at, to be able to write good code, because those libraries were in their infancy when I started using them. Okay, so sometimes it takes a lot of patience to read through code, okay, and to understand what's happening. Check all inputs. These are the basic rules. These are the key ingredients. Again, another thing why scikit became very, very popular is because it has terrific user guides. Lots of example code, beautiful documentation. It's very good. Again, you can read, there are tons of user guides for scikit-learn. Again, lot of good libraries, they're well implemented and they come with brilliant documentation. This is all the documentation, right? So remember that every library has their unique way of performing a bunch of operations. Scikit-learn has its own unique way. We will learn that and we'll get used to it as we see examples. Every library, the way NumPy does a bunch of operations, it will be very different from how scikit-learn does, right? The way, just look at Seaborn. The way Seaborn does or the way Matplotlib does a few operations is very different from how NumPy does, right? So the way Pandas does is different. So every library has its own quirks. And we'll have to learn that by reading examples, by experimenting and things like that, right? If you want to learn for any technique, just say sklearn PCA. You don't have to type whole scikit-learn, because sklearn is the module name that is used extensively for all classes, functions that are there in scikit-learn, right? So if you want to read more in depth, right? If you want to read more in depth, you can learn about scikit-learn classes with a bunch of examples here. Okay. First and foremost, we have a data now. Let's take it. Okay. Is this data pre-processed in the sense that, again, the term normalized and standardized can be used in different ways. Okay. For example, if you go to Wikipedia, I've copied here it from Wikipedia, right? I've literally copied it from Wikipedia. What does Wikipedia say? Wikipedia says that, okay, again, I've copied it from the Wikipedia article for principal component analysis. It clearly says that, okay, PCA can be done blah, blah, blah using eigen decomposition, and usually after the normalization step of the initial data. The normalization of each attribute, which means each feature, consists of mean centering and subtracting each data value, etc., etc. In addition to that, it also each variable's variance, making it equal to 1. So Wikipedia defines normalization. Again, what some people call normalization, some libraries call that as standardization. Right? So this is a very, very misused and overused term. So don't get caught up with it, understand what it's doing. What you have to do is, if you read Wikipedia, it simply says that you have to do mean centering and you have to ensure variance scaling such that each feature variance equals to 1. That's what it means. Now mean centering and variance scaling in scikit-learn is called standardization. Okay, let me show you this. So pre-process, where is this library? Sorry. So I think I linked it somewhere. Just give me a second. Okay, so anyway, let me show you this subclasses user guide. I can just show you here actually. So sklearn pre-process. Okay, so there's a very nice tutorial on pre-processing data. Look at this. What does scikit-learn call? Scikit-learn calls standardization as mean removal and variance scaling. The same thing Wikipedia calls it as normalization. So don't get confused by this term. Understand what we have to do is mean removal and variance scaling. Simple, right? Again, it says how to do it. The best part about scikit-learn is it gives you some simple code to do it, right? It's very good. So all of the data pre-processing, I'll show you some code. I'll go back to this. Look at this. All I've done here is, if you're a beginner, just read it. It says, okay, from sklearn import pre-processing. So there is a module called pre-processing in sklearn. Sklearn basically means scikit-learn. Then there is this numpy array. And then it says preprocessing.scale. And it gives you scaled. That's it. In one line of code, instead of you, again, you can implement this standardization on your own, right? Again, it's important. Again, it's not rocket science, right? All you have to do is, given a data matrix like this, the foundational concept is important. Given a data matrix like this, go to every column, find the mean, subtract the mean from all the values, and ensure that the variance equals to 1. It's a very simple concept, right? You can do it. You can go, if you write NumPy code, you can go column by column and perform this operation. But why should you write a code with for loop, all of that, when somebody already gives you this, most likely very good implementation of it? But if you do not understand how it is done, because I've asked this in many interviews. People say, okay, I'll pre-process using scikit-learn so-and-so function. I say, okay, cool. In lot of coding rounds, I say, okay, can you just implement sklearns? Please implement sklearns standardize function. This function. Scale function, not standardize. Scale function. Okay. Can you just implement it in NumPy? This is often, again, I ask this very simple stuff in coding rounds. Because if you know NumPy, again, I tell him, okay, if you need some help, you can always use a browser to get help. And I keep watching him on the screen share, or I sit next to him and see how he's writing code, right? I want him to understand how this works, and I want him to be able to implement in NumPy. Then I'm confident that he understands NumPy. Most importantly, he understands the mathematics behind this, the operation that he's using. Black boxes do not help, right? Again, there are multiple ways of pre-processing. Okay, there is also 0-1 scaling. Okay, so there is this concept called 0-1 scaling, or also called as min-max scaling. We discuss in our course videos as min-max scaling. This is another operation. In this context, we'll be doing mean centering and variance scaling. Cool. So what do I have? My data is data. I just looked at this. I just looked at this 5 lines of snippet. I understood what is happening. If required, I'll go read the documentation for this. In this case, I don't even need it. I just get my data scaled. Cool. Once I have it, I just want to make sure that the shape of it is sensible, right? I just want to make sure that the shape is sensible. Yes, the shape is sensible. I also want to plot the standardized data to see how it is. Again, standardization of data will change the image. So what am I doing? Again, I'm taking the 10th row from the scaled data and I'm just plotting it using matplotlib. This image is different from this image. Don't forget, this image is the regular image, right? But after standardization, the colors will change, or after mean scale. So instead of using the word standardization, I'll just say mean scaling, mean centering, variance scaling. Okay, that is more like clear what I'm talking about. The colors will change, but that's okay. We know that. That's a transformation of data. We know that for sure, right? So let's just do that. Okay. So yeah. So what I meant was mean centering. I think I should be careful. What I meant was mean centering, variance scaling, not mean scaling. Okay. So let me be precise here. Mean centering, variance scaling. Okay. It's a mouthful, but I wrote it here also that it's mean centering, variance scaling. Cool. Now I have standardized my data, or I have pre-processed my data. Okay. So from my data, I got data scaled. Okay, which is normalized with centering and scaling. Okay. Of course, centering always is with min, scaling is always with variance in this context. Cool. Now, how do I compute PCA? If I don't know how to compute PCA, it's just a Google search away. Again, look at this. sklearn PCA. Okay. Oh, there is already a function called PCA. Okay. So it's in scikit-learn decomposition PCA. Now, again, as I told you, scikit-learn has its own little nuances, right? Okay, let's go into it, right? So again, what does it say? Try to understand as many parameters as possible. If you do not understand a parameter, somebody asked me a while ago, right? What is number of components? So I want to compute PCA and I want to retain only these many components or these many eigenvectors. Now, what does copy equals to true mean? Again, we have discussed this in the course videos. I've discussed each function's all the key parameters, if not all the parameters. I've discussed this in the course videos. That's why I'm avoiding it here. Copy, what does it do? Whiten, what does it do? SVD solver. I told you, right? There are lots of SVD solvers. There is randomized SVD solver that I was talking to you about. I think it's also mentioned somewhere here. Where is this? So they also publish a bunch of research papers that are relevant here. Where is this? Where is this? I remember reading it. So RPAC randomized. Okay, look at this. So it says, when it says randomized, it uses the Halko et al.'s paper. This is a very, very popular paper, beautiful paper, Halko SVD randomized. All right, so it's a superb paper. If you notice, this paper was written in 2010. It has over 2,400 citations. It's a very, very good paper. Again, it's fairly complex mathematically. It's not a trivial paper to read. You have to have some background in randomized algorithms. You have to have some knowledge of internals of how SVD itself works, etc. So I enjoyed reading this paper because I was a student then, or just graduated from college, and my master's thesis was all on randomized algorithms for optimization problems. I really loved this paper. I think this came in late 2010. Yeah. So in 2009, I graduated. My master's thesis was how do you do randomized algorithms for optimization problems that you encounter in support vector machines. So this paper I really loved and I enjoyed it. Of course, it's not necessary that you should be able to understand every algorithm. Like there's so many algorithms that I don't understand because nobody can be expert in everything. I know the basics of most things, but not in depth of everything. Okay. So somebody says, why are we doing pre-processing? I think you should watch the course videos. Okay, please. Okay, we have covered it in course videos. It's also there in the comment section of a lot of videos. Please go watch it. Okay. Sounds good. As I mentioned, we'll do more code walkthroughs. It's a good question. I really appreciate that question, but you should check out the course videos and the top 5 comments under every video because we covered that. We actually answered the exactly same question. Cool. So, okay. So how does PCA work? Okay. There are all these parameters, all that. The good thing here in scikit-learn is they write some simple code like this. They take simple matrices like this. This is a simple matrix and they show you how to compute it. Now look at this. So when I create, but again, for you to learn scikit-learn, there are 2 great things. First, look at these simple examples. I think every major function in scikit-learn has this documentation. That's why I think it became extremely popular because it's easy for people to learn from. And this documentation that they have for every parameter is also very, very good. And for every function, they have multiple projects in which they have used this. They have used PCA in all of these more detailed examples, right? So there is so much to learn from just this one page. Okay, so first things that I learn by just looking at this, look at this. I say PCA something, okay, number of components equals to 2, cool. Which means I'm trying to project it into a d dash dimensions where d dash equals to 2. Now I have to call this function called fit. Look at this, there is this function called fit. So if I go to the documentation, there are all these, okay, so here this is PCA's constructor. Okay, this is PCA's constructor. This constructor, I give a bunch of values that I want, right? So these are the parameters of the constructor. Then there are a bunch of attributes of the PCA object that I have. Right? Again, read up about these. Then I have a bunch of functions or methods that this PCA object can call. Okay, you have to read through this. If you want thorough understanding, try to understand at least most of this, if not all of it. Understanding all of it is too ambitious, but try to understand the basics as a beginner first. Okay, could I zoom in a little bit? Okay, I'll try to zoom in a little bit. Okay, I hope this helps. Okay, I zoomed in a bit. Thank you. So now let's see this code, right? So first I want to try. Imagine I'm a beginner. I'm just importing. So I've just looked at this code. I mean, this code is super simple to follow, right? This code is super simple. All that they're doing here is they're importing a bunch of libraries. They're created an NP, a NumPy array or a NumPy Andy array, and they're initializing a PCA object using PCA constructor, and they're calling the fit function. Then they're able to print what is the explained variance, all the singular values, eigenvalues, they're able to print all of that. Cool, very good. So by just looking at that simple one example, I can start writing code. Okay, let's go step by step. Okay, so I'm importing PCA. I want my PCA and the number of components that I want is 50 components, which means I want to project the data from D dimensions to D dash dimensions where D dash equals to 50. For that, I need 50 eigenvectors. I need 50 eigenvectors for this, right? So the number of components basically means that. Okay. So I also want to time things. Okay. Remember we have seen this in one of the previous sessions. You can just import time, start time, end time, and you can print the time difference. We've already seen this in the previous sessions, right? So what am I doing? I'm saying, okay, my data, see, look at this. As soon as I get this, I want to understand what is this data type. So if I print PCA, what do I get? If I print PCA, I get a PCA object with all these parameters. Okay, then on this PCA, see what is this? This is a PCA class and this is a constructor and I'm returning a PCA object. Lowercase is the object, uppercase is the constructor. Now on this object, I'm running this fit function and I'm passing the data scaled. And this whole thing, when I ran it, it took about 7.47 seconds. 7.47 seconds, yeah, roughly about, or 7, yeah, I think it's 7.47 seconds. It took a few seconds. Oh, how did we get d equals to 50? You can, again, this is called the hyperparameters of the model. I'll tell you how to choose this hyperparameter in a few minutes. Again, if you're asking this question, most likely you have not watched the course videos, because we explained that based on variance explained. I'll tell you, right now I'm just picking 50. I don't know what is the right value. I'll show you that step by step. Okay, cool. So next, the first thing that I want to understand here is these 50 dimensions, how much is the variance explained? We discussed about variance explained, right, in the course videos. If you want, I can open that. AppliedAICourse. We explained this. There is a specific video just explaining this part. So principal component analysis, okay. PCA for dimensionality reduction, right? So in this video, we explain how to compute the, how do you explain information or variance explained, and we also have a IPython notebook where we walk you through code, right? It's the same thing here, right? Again, what I'm doing literally is what I've explained mathematically and with some code example, I'm repeating the same thing here in Colab. That's it. Okay. So when I print the variance explained, okay, this basically says my first dimension, right, or my first eigenvector, how much variance is explained. Again, mathematically, PCA is trying to explain the whole variance using a few dimensions, which are nothing but your eigenvectors. So let's do one thing. So when I start printing them, if I print my variance explained, I get this. My first feature explains 26% of the variance. My second feature explains 5.6% of the variance. My third eigenvector explains 5.1% of the feature of the variance. My fourth one explains 3.95, so on and so forth. Now, the question here is, okay, I want to use the data from d dimensions to d dash dimensions such that there is minimal loss of information, right? That's the idea, right? So let's plot this. So what am I plotting here? Again, very simple plot here. All that I am plotting here. This is just simple matplotlib. Matplotlib, I'm saying I want to plot this variances, right? I want the grid to be on. I want my x label to be component. On my x-axis, I want the label to be component. I want the grid to be present. My y-axis is variance explained, and show the plot. So as soon as I run this, I get this plot. Again, some of this is not visible. Here I have component. Here I have variance explained. I don't know why it's not fully visible here. I also have the grid. So first thing that you learn is that the first few features or the first few eigenvectors explain most of the variance. The top eigenvector explains over 25% of the variance. The moment you come to the 10th eigenvector is roughly here, right? It's roughly about 2%. After that, it's all very, 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 very small. So the data itself is 1140 cross 62,500. What is the minimum of both of them? It is this. So you can project this data into 1140 dimensions, which means you will get 1140 eigenvectors. The top 10 eigenvectors almost, look at this. This is called the inflection point. Okay, again, we can find the inflection point more precisely, but in general, you can say, I want to use those many dimensions such that 90% of my variance or 99% of my variance is explained, right? So again, if you do not know this, you should watch this video where we explain this in detail. It's publicly available. I'll avoid covering some of the theory concepts that I've already requested you to watch. Cool, sounds good. So the next thing that I want to see is, somebody says it will be visible if you use light theme. Oh, good. Okay, I do not like the light theme because it's too bright for my eyes. Good, thank you, Patra. Thank you very much. Subhadeep, sorry. Yeah, I think it's just the dark mode and light mode. I always use the dark mode. Anyway, sounds good. So now I want to do one other thing. I want to see, look at this. This is my data, right? I'm trying to, suppose if I use my d dash to be 50. Again, how do you pick the right d dash? I just picked a number which is reasonable, but ideally you should pick this d dash such that 99% of your variance, some high number, 99% of your variance is explained by these 50 top eigenvectors, right? So that's how you pick. That's one of the heuristics to pick it. I did not go through that because I explained that in the course videos anyway. So I said, okay, let me just pick 50, which seems reasonable. Now what I want to see here is this. I have 50 eigenvectors, right? So let's say eigenvector 1, 2, 3, so on and so forth. I have 50 eigenvectors. Now each of these 50 eigenvectors are also, if you think about it, these eigenvectors are in the same space in which the images are there. Images are in the 65,500 dimensional space. This is the space in which my images are. These are vectors. The eigenvectors are also vectors in this dimensional, in this extremely high dimensional space. Now, if I want to visualize these vectors, again, this is also a vector, right? This is basically 1 cross 62,500. I can always reshape it and say 250 cross 250 and I can visualize it. When you visualize it, they're called as eigenfaces. Actually, so this visualization is called as eigenfaces because this is basically visualizing faces in the using the eigenvectors. So eigenfaces was one of the first or one of the earliest techniques that was used for face detection and recognition. This was one of the oldest, I don't remember exactly when this paper was published. It is one of the oldest ways in which face recognition is done. So somebody is talking about elbow rule. Yes, I can determine D dash two ways. I can either find the inflection point using the elbow method, or I can say, okay, I want to conserve or preserve 99% of variance. You can apply any of these two methods. It's better to apply this than the elbow method in this context. Cool. So this whole concept, there is a whole concept called eigenfaces, which is one of the first algorithms that was used for face recognition. It never worked as well, to be honest with you. Okay, I'll tell you how it works in a minute. So what I want to do is this. So if I say pca.components.shape, remember the PCA object that I just showed you, right? So sklearn PCA. The PCA thing that I showed you, the PCA object has something called as, look at the attributes. It has an attribute called components. These components are nothing but the principal axes in the feature space representing the directions of maximum variance, which is nothing but your eigenvectors. That's what it is, right? So, this is just the explanation of eigenvectors to our problem of PCA, right? So, PCA.components.shape, I want to see what is the shape of them. So, I realize that because we try to get 50 components, I get a matrix which is 50 cross 62,500. As I just told you, right? Every vector here is a vector of 62,500 and I have 50 such vectors. And that whole thing, whole of this is actually stored in a data matrix, and the data matrix I can get using PCA.components. Look at how simple scikit-learn makes our life. Okay, but don't get fooled by simplicity. If you do not know the internals how it works, all this simplicity is useless. Okay. Next, okay, now what do I want to do? I want to see all these images. How do I see these images? It's very simple. Okay, so pca.components.shape gives me 50 cross 62,500. So I'll just write a for loop and I'll keep I am showing all the images. Look at how I do it. For I in range, PCA components shape 0. Shape 0 basically means 50. Because there are 50 images. Okay, I think I did not do any operation, so let me just reconnect it. Okay. So, okay. So there is a shape object here, and so I'm just going from I equals to 0 to 49 because there are 50 components here. If you want to plot multiple images one below the other in matplotlib, there is this very simple mechanism. Okay, just say figure equals to plot.figure and use this I. This will create the ith figure for you. Now you can say, look at what I'm doing here. I'm taking the ith vector, ith component here. I'm taking the ith eigenvector, reshaping it into 250, 250, and I'm calling it IM. After I do that, I'm just plotting it using IM show. Color scale gray, and I'm just putting a title to each image, saying the title is I transformed to a string. That's it. Very simple, just this small snippet of code. I'm just iterating through each of the eigenvectors and I'm showing them. The moment you show them, there's a very interesting observation here. Let me go one by one. Look at the 0th one. Okay, this is what is explaining almost 20% of the information in my images. This is explaining almost, I think 26, 27%, roughly 27% of the information in my images. What does this look like? This looks like a typical human head. Look at this, typical shoulders, typical human head. There are some features of eyes, maybe a little bit of nose and mouth. So because all of our images are faces, right? All of our images are faces. It says I can represent most of the information by using an example image of a face which looks like this. So, I mean, it's such a brilliant idea. The moment you say this, if you show even a 3-year-old kid, what is this? He says it's a person, right? So your PCA in this huge complex 62,500 dimensional space is able to figure out that all these are in general faces. That's the first. That's the first. Look at the next. Where are all the highlights? The highlights are near the eyes. The highlights are near the mouth, right? And everything outside this. So the second eigenvector is trying to say that there is some eyes here, there is a mouth. It's trying to capture that information. The third eigenvector, now it's trying to capture something around the shape of the face and the hair structure. The fourth one is trying, again, look at this. It's trying to capture hair on the left side. This is trying to capture hair on the right side. Again, this is trying to capture the light that is falling here. If you go a little down, right? Look at this. If you go a little down, you'll get all sorts of, again, they look like ghosts. Please don't worry. This is looking as if there is a forehead to everyone. Okay. So this basically shows that there is a forehead and there are some dark patches below that. Okay. So they look like ghosts, but in an essay, oh, this looks like actually, oh, wow. This looks, again, the moment I see this, this looks like George W. Bush, right? This looks like George W. Bush. I think there are lots of images of George W. Bush. That's why it looks like George W. Bush. Because there are so many images that this is a standard template. Again, the word that is often used is that this is a template image. Now the interesting part is this. Given my data, look at this. Given my data, which is in 62,500 dimensions, using this simple PCA concept, I've projected it into 50 dimensions. These 50, again, these dimensions are different. Suppose if these are my dimensions, the dimensions I have here are different. These 50 dimensions are not a subset of the 62,500 dimensions. But if I create a new space, okay, let's assume this is space 1. This is a completely different space of 50 dimensions. But I can represent each face wherein each dimension represents some aspects of face. Okay, each of these dimensions represent some aspect of face. And now I can represent any face using just a 50 dimensional vector instead of representing it using a 62,500 dimensional vector, right? So this is what you get, right? So again, this concept, I think they used it even in early 90s. I don't remember when the eigenfaces paper was written, but it was one of the oldest papers that was built for face recognition. Now I want to understand one thing, okay? All this is cool. Now I want to see, so this is my original data, right? This is my original data, original scaled data. Now this original scale data, if I multiply, again, what is my original scale data? It is n cross d, right? Let's not forget that, right? This is n cross d. This is my original scaled data. Let me call it ds. Now if I multiply this ds with my eigenvector, with a matrix that I construct using my eigenvectors such that this is d cross d dash. Look at this. If this matrix is d cross d dash, when I multiply both of them, what do I get? I get an output matrix. Let's call this output matrix as y. Let's call this output matrix as n cross d dash. Now here, what is this? This is d cross d dash, which means there are d rows here. Look at this. What is the dimensional? Each of these eigenvectors that I have here, each of these eigenvectors, the 50 eigenvectors, each of these eigenvectors is 62,500, right? Each of these eigenvectors is 1 cross d. And I have d dash eigenvectors, right? So now what if I do this, okay? So I have d rows, right? And d dash columns. In each column, if I place the ith vector, look at this. In each column, in this matrix, each column, I'm placing the ith vector or ith eigenvector. The moment I do that, what do I get? This matrix, the number of rows will be d, the number of columns will be d dash because there are d dash eigenvectors or components that we're using. So I can project the data from the d dimensional space to d dash dimensional space using this simple multiplication. So I can actually implement this using this multiplication. But we don't have to even do that because scikit-learn does that for us. I can just say, I've already built my PCA. I've already fit my PCA model. Now I'm just saying PCA.transform. So given this data, what it's literally doing internally is, given this data, it is simply multiplying with this matrix and returning this. That's all it is doing. Okay. But instead of us doing it and making mistakes in the process, you can just call the transform function. Now the transform function is 1140 points one corresponding to each image, and each image represented using 50 dimensions. But the problem here is this. Can I visualize 50 dimensional space? Can I visualize a 50 dimensional space? I can't. Okay, I can only visualize 2 or 3 dimensional space. 2 dimensions is better, as we discussed in the course videos, right? So let me retrain. So I'll try to get a 2-dimensional embedding, and I want to visualize this. It's very simple. So PCA, so I already have this PCA variable, right? Remember, I already have this PCA variable, which is an object of class PCA. I'm just changing its number of components to 2, right? Because I want to get a 2-dimensional representation so that I can plot it with one axis on this, one dimension here, other dimension here. I want to see it as a 2D plot. How do I do it? It's very simple. I change the number of components to 2. Now there is another function. If you go through the documentation of scikit-learn, there is a function called fit transform. What it does is it first computes the eigenvalues, eigenvectors using the fit function, and then it transforms this matrix and gives you this y. So it first computes the eigenvectors and does all of this in one function. Right now, what do I get? I've taken my data scaled, I've fit the PCA with number of components equals to 2, and I've transformed it. So now my data 2, if you look at the shape of data 2, 1140 points, each point corresponding to one image and two features or 2 dimensions for every data point. Now I want to visualize this. Okay. One thing, this is a very common mistake that we have seen people do in assignments. People just say, okay, matplotlib, I just want to do a scatter plot. Because anyway, what does my data matrix look like? My data 2 looks like this, right? My data 2 looks like this. I have n images, one row corresponding to each image, and I have 2 columns. So let me plot this as x-axis, plot this as a y-axis. Again, matplotlib has a scatter plot function where this has to be the x-axis, this has to be the y-axis. If you don't know this, I've just given you the function reference. You can just check it out. But the moment I show this, I get just a blob of points like this. I can't make head and tail of this. I just can't make sense of what's happening. What is the right thing to do? The right thing to do is, I want to color each of these points. I want to color each of these points such that all the points belonging to the same person or the same folder should get the same color. Now look at this. This is where the metadata is useful. Look at my data. My data 2 looks like this, right? My data 2 has n rows and it has 2 columns. When I plot this data, this I'll use as x-axis, this I'll use as y-axis. Okay. Now for any ith row here, I have my labels. I have my labels list that we created as metadata very early on, if you recall. I mentioned this here, right? We created the labels here, right? Now what I'll do is this. I'll say labels I will contain the folder number to which this belongs to, right? So what I'll do here is I'll color each of them. I'll color each of these points because I want to color all the points belonging to the same person or folder with the same color. And that information is there in my labels list. That's why I've created this metadata. Okay, that's important. So again, somebody is asking questions which are irrelevant to this discussion. Hence, I'll not be able to answer it. Okay, because I also want to cover this. Again, I might overshoot this discussion by about 15-20 minutes. If you guys are okay, I want to continue so that we can finish this whole discussion and not have to postpone it for tomorrow. Okay. So, okay, sounds good. So let's get into it. So I've written this simple function called plot embedding. Again, I have taken a plotting function that is there in scikit-learn and I've modified this code. This code is very simple. Look at it. This plot embedding, the way I want to do it is this. Given some data matrix X, look at this. This data matrix X is nothing but, my data matrix. Y is nothing but my labels. Okay, I want to get both of them. And whatever title I want to give to this plot, I want to get it here. First, what I want to do here is all the points in X. Look at this, all these points, because I want to plot it. See, look at this. I want to translate this into a plot, right? So look at this. I want to translate this into a plot. I want the plot not to have too much x-axis, too much y-axis. I want the x-axis to be between 0 and 1 and y-axis to be between 0 and 1. Okay, just so that it's contained. Because if some x value is very large, my plot will keep going to the right. Or if some y value is big, it will keep going to the top. I want to contain that. So what am I doing here? I'm just doing some simple min-max scaling. Again, this is something that we have discussed in the course videos, right? I'm just doing simple min-max scaling. Okay, so that my plot, when I plot this, so that all these points are in the range of 0 to 1, all these points are in the range of 0 to 1. So that it's easy for me to plot. Next, what am I plotting? I'm just saying plot.figure. Next, in the figure, look at the plot that I get by the end of it. This is the plot that I want to get by the end of it. For every data point, look at this. For every data point I want this to be the x-axis. I want this to be the y-axis. At this point, if labels I equals to, let's say, 3, I want to show this text 3 at this coordinates. That's what I want to do, so that it's easy to visualize, right? So how do we do it? The matplotlib can also show text. Say text. Where do I want to show this text? At this coordinate, because it's ith point. Look at this. What am I doing? I'm iterating through each of the points. I want to show the ith point, right? This is the x-axis, this is the y-axis. What do I want to show? I want to show yi. Yi, again, remember, x is nothing but your data 2D. Your y is nothing but your labels, right? So whatever label is there, I want to represent it using a string, and I want to color in such a way that the color is also based on yi. So all the points which have the same yi, which belong to the same person, get the same color. Very simple. This is just a simple for loop for plotting. Next, if title is not none, just add the title. Otherwise, just leave it. Now, I'm just calling this function. Look at this. This function is called plot embedding. I'm just calling this function and I'm saying plot embedding, x equals to data2, y equals to label, and I want the title to be PCA 2D embedding. Now, when I do this, again, 2D data is easy to see, right? Oh, this is the embedding that I get. Okay, this is a mess. Okay, look at this. What do I want? Ideally, what should it look like? All the points which are 0 should have grouped together like this. Ideally. I mean, the real world is never ideal. All the ones which are 1 should have grouped together like this. All the ones that are 2 should have grouped together like this. But that's not how this works. Okay, this is a mess. There is some pattern here that 3s are all here, but somewhere here everything is a mess. I can't make head and tail of this. Okay, so PCA for this task, for faces, if you go from the d-dimensional space to the 2-dimensional space, and if you visualize it, the visualization is useless, right? But what people do is, people go from d-dimensional space to d-dimensional space, and they build models on it. They build machine learning models on it, like support vector machines, logistic regression, etc. If you don't know these, don't worry, but I'm just trying to connect the dots. Now you might wonder, the first question, it's a very popular question that I used to ask people, which is, why don't you just build a model on the d-dimensional space itself? Right? Why don't you build, let's assume I'm building logistic regression. Why should I build my logistic regression model in the d-dimensional space? Why can't I just build in the d-dimensional space itself? Right? So a lot of people say, given a data, I'll first do PCA and then I'll build a model on it. That's not always the best strategy. Again, if the modeling method that you're using does not work in high dimensions, because this is typically very high dimensions, this is typically small, right? Typically 50, 100, some small number like this. So if the modeling algorithm that you're using works well in high dimensions, nothing stops you from building a model in the d-dimensional space. But if the modeling algorithm, for example, imagine if you're using some form of trees, like decision trees, they work very well when the dimensionality is small. In such a case, it makes complete sense to do PCA and then use some tree-based algorithm. But if the algorithm that you have, let's assume you're using logistic regression, that can work fairly well in high dimensional spaces. In such a case, there is no point in doing PCA and then applying the model, right? I hope, again, this is something that we discuss in our case studies when we actually encounter problems like this. Cool. So again, those of you who want to see it, again, here is a nice example. You can go here. Those of you who already know other machine learning techniques, here is a nice example where, again, the code is also fairly readable given that you have some basics. What they do is this, what they do in this code is this. They first take the same image data, d dimensions. I think they projected it, I think 50 dimensions, right? Which is d dash. And then they train an SVM on it. And they show the results here. Again, we can never guess whether the results here will be better or results will be here or better. Okay, sometimes results here can be terrific. So it's always a good idea. Why not? If your algorithm, performs well on lower dimensional data, just try it. Okay, so this whole process is shown in this example which I've listed here. So those of you who are interested who know already other machine learning algorithms can go through this. If you don't know, don't worry. We will revisit this concept over and over later on, right? So, okay, somebody says we could overfit. Okay, that's a good point actually. So let me go here. Where is that? Okay, where is this? Okay. Where did I draw this? Okay, so I think I drew it here. Okay, so one very important point that somebody brought up is, if you have too many dimensions, won't we overfit the model? No, if you use your regularization smartly, the whole purpose of regularization is not to overfit. You can use a strong regularizer like L1 regularizer to ensure that you're not overfitting. Just give the regularization coefficient a larger value, right? So if you're careful with your model, you can avoid overfitting to some extent. It's a good point, right? Cool. Again, I'm not saying you should always model on D or you should always model on D dash. There are instances where modeling just on D dimensions is a good idea. There are instances where modeling on D dash is a good idea, right? I can argue on both sides. In the real world, my suggestion is this: try to model in D dimensions, try to also model in D dash dimensions, see which of them works best, because instead of being opinionated, let's look at the reality. Given a data set, where does it work better? And that is the absolute truth, right? So that's important. Cool. So since we have discussed this, I know we are close to 8 p.m., but I thought we can cover t-SNE also because we've explained a lot of details about t-SNE in the course videos. Again, we will revisit the t-SNE's optimization problem. So t-SNE has an optimization problem that we have not discussed in the course videos in the t-SNE chapter, because we thought we'll cover it at a later point of time after we learn optimization algorithms, right? So I'm not going into in the course videos in the t-SNE chapter, we have given the intuitive understanding of t-SNE without going too deep into the optimization part because it is complex. We'll do a session just on the optimization part of t-SNE at a later point of time. Cool. Now imagine t-SNE is another technique. We have discussed in the course videos how to use it, right? 62K dimensions, not too high. You can train. So somebody says, isn't 62K dimensions too high for logistic regression? No, you can train, if you're careful with your logistic regression, you can train even with 62K dimensions, and you can do it. Don't worry about it. You can do, if you're very careful with your regularization. Again, without regularization, you will mess up the whole thing. Okay, again, we'll discuss this when we arrive at logistic regression. I'll show you examples where even with hundreds of thousands of features, you can train logistic regression if you're careful with it. Okay, in the interest of everybody who may not, and everybody may not know logistic regression, so let's continue here. Cool, so let's go to t-SNE now. Okay, now again, we have discussed how t-SNE works, how t-SNE works in various cases. We've also discussed about nice blogs, and we've explained some of the concepts using those blogs, etc. The beauty of scikit-learn is this: you can go from PCA model to t-SNE model in literally one line of code. It's one line of code change, literally one line of code change. But I also want to show another thing. See, in this example, in the example just above, what have we done? We have taken the LFW dataset, right? The people dataset, and we manually processed it ourselves. And I've shown you step by step how to process it manually, how to convert the image to NumPy matrix. I've done it so that you understand how to process images, how to do it manually. But what scikit-learn does is, it already has this dataset for you. It already has this dataset, so you don't have to worry about it. So scikit-learn has the popular datasets that are publicly available. There are tons of datasets like this, right? So if scikit-learn datasets, okay, so okay, datasets, okay. So scikit-learn has tons of, okay, dataset loader, okay. So there are all these datasets. There are tons of datasets actually in scikit-learn, so that you can try out scikit-learn faster. So scikit-learn also has this LFW people dataset. It also has a function called, again, you can read the documentation here. It also has a function which says, okay, you can fetch the data from LFW people where minimum faces per person is 100. Okay, it already gives you that. Okay, let me just show you that documentation. Again, but I wanted to show you how to do it manually. In case this dataset was not available, how would you do it? Right? That's important skill to learn. That's why I went through all that part. So scikit-learn datasets fetch LFW people, right? It says, okay, where do you want to get the data from? It will directly download from the internet if you want. whether you want to resize. By default, resizing is 0.5 because they're resizing the images so that it's easier for people to pull from. Minimum faces per person. Again, you can read this documentation. If I want, so in my code snippet, I said I only want to fetch data for those people who have minimum 100 faces. Now look at this. The moment just with 2 lines of code, I got the data set. But please understand that in the real world, all data sets that you care about may not be in scikit-learn, right? So you should learn how to load data sets yourself, the way I've shown above. Now I want to see what is the data type of D. Oh, so the data type of D is not a NumPy matrix. It is some sklearn utils bunch. Now what is D now? Look at this, my input, okay, I called this function, this part was simple, but I was expecting a NumPy matrix, right? But what I got is some special data type. Now that's why you should always read the documentation, which is, where is this? Okay. Okay, I have the link here. Let me just go here and copy the link directly so that it's easier for us instead of searching again. Okay, let me just close these, let me just close some of these. Okay, so fetch people, look at this. It generates, so the documentation is very well done. These are the number of classes, these are the total samples, these are dimensionality. Again, the dimensionality here is different because they're resizing the data. And they might be using a slightly different data set from us in terms of the image sizes, right? Okay, cool. So what does it return? It returns a data set, which is a dictionary-like object. And if you want the NumPy, look at this, what it returns to us is a data set, which is a dictionary-like object. And if you want the actual data matrix, you can get it in dataset.data, right? If you want the NumPy array of, if you say dataset.images, right? Dataset.target, this is what we stored in our labels, right? Whatever we stored in our labels is being generated here using dataset.target, right? So what it returns, what this function returns is not just one NumPy array. Along with NumPy array, it also gives us multiple metadata, right? And again, the code here and the examples, again, you can go here, look at the example code, explains everything. The beautiful part about scikit-learn is the amount of documentation. It's terrific. So my type D is bunch. Again, always check the data types. If I want to get the data, so d.data I know gives me the data. The data.shape, yes. 1140 images, we knew this because minimum number of faces equals to 100. When we loaded the data ourselves, we got 1140. Here also we got 1140. But the columns are fewer here because by default fetch LFW, by default fetch LFW resizes the images by default. You can say resize equals to 1, then you'll get larger images. Okay, if I want to get the shape of each of the images, I can say d.images.shape. This basically gives me the number of images, the height of each image, and the width of each image. Because in the description, if you notice, dataset.images gives me NumPy array of shape, these many images, the rows and columns. Right, so these many images, the height and width of each NumPy array. So each image. Cool. All that is good. Okay. So given this data, see, look at this. I just loaded the data in like 2 minutes instead of doing all the code here. Again, I'm just showing another way of loading the same data in case you want to experiment faster. But it's always an important skill to be able to do it on your own. Okay. So now what do I want to do? Given d.data, I want to pre-process it. Again, we have shown how to pre-process using scaling, right? I just pre-process it and I'm calling it as X. What is the shape of X? 1140, 2090, 2914. And I'm calling Y as d.target. So what is my X now? X is the data which is normalized. Y is all my labels or target. In this documentation, they call it target. We called it labels, right? Now I want to understand a couple of things. Okay, I want to say for each of these, again, remember, for each of these, so my Y contains all the labels, right? Folder names basically, or folder numbers. So I want to get the frequencies of each of them. So folder 0, there are 236 images. Folder 1, there are 121 images. Folder 2, 530. Folder 3, 109. Folder 4, 144. If you don't know how to compute frequencies, just Google search for it. You'll get this snippet. Again, this is standard NumPy, right? Imagine if you have a list, right? Look at this. np.unique will give you all the unique values and the counts. I'm just converting that into a NumPy array and printing it. That's all. So numpy.unique helps you find, given a list like this, or this is not a list, this is an ND array, I'm sorry. Given an ND array or a array of NumPy, it tells you how frequently each of these occur. Simple. Now once I have that, I'm running tsni. Again, my number of components equals to 2. Again, the tsni documentation you can read up here. I've also described this in the course videos. Okay. So number of components equals to 2. Again, you can skip some of these things. Initialization equals to PCA basically means, remember that tsni has to solve a complex optimization problem. Right? In all optimization problems, there is something called as the initial value. Again, we'll discuss this when we learn optimization algorithms. It will use the initial value after computing the PCA. Again, that's not the final value. It computes the TCA. It computes tsni by using PCA as the initial value in the optimization. If you know optimization, you will understand it. Otherwise, we'll discuss about initial values when we go through optimization sections. Again, we discuss that in the course videos anyway, but we'll also do it when we do code walkthroughs. Cool. I'm just running this. Okay, look at this. My tsni is so simple. First, I create a so within sklearn, there is manifold. Within manifold, there is tsni. This is the constructor. You can look at the documentation. There are many other options, but let's use the simplest one. I can skip the random state because tsni uses some randomization actually. Tsni uses some randomization. Again, we told this, right, in the course videos also. It's a stochastic algorithm, which means it uses randomization. By creating random state equals to 0, every time I'll get the same output. This is like your random seed that we have seen in the previous sessions, like NumPy random seed. This does the same job. Cool. So I'm just starting time. Look at this. What I want is, I want it to do this, two things. Given this X, again, it's the same syntax that we've seen for PCA. sklearn is extremely consistent. Look at this. First step, you call the tsni constructor, create a tsni object. Then you say fit transform. What does fit transform do? First, it computes tsni on X, and then it projects this X into two-dimensional space because my number of components equals to 2. So it first fits and then it transforms. It first fits the tsni model and then it transforms. Now, how much time does it take? If you look at this, it takes 17.5 seconds. Cool. Now what I want to do is this. Now there is this parameter. If you go to the documentation, where is tsni documentation? Tsni sklearn. There are a lot of parameters here. Many of the important ones, like perplexity, we discussed in the course videos, how perplexity works, how number of iterations will transform the output. All of that we discussed in the course videos. There is one which is number of jobs. I think I discussed this also in the course videos, but this is important in this context, especially from an implementation concept, because number of jobs will just implement parallelly. So instead of doing just using one core, it will use multiple cores that are there on your computer, right? It's like parallel processing. Again, scikit-learn even lets you do parallel processing for computational intensive stuff. So initially I did not use anything. It took 17.5 seconds. Then if you read the documentation here, if n jobs equals to -1, look at this. -1 means use all processors. So if I just use n jobs equals to -1, it will try to use all the processors. Instead of 17.5 seconds, it took 14.7 seconds. Not too much of an improvement. I also tried how much time it will take if I use 5 processors, or if I create 5 jobs out of it. Again, this is just multiprocessing, right? It takes about 14 seconds, not much improvement, right? Again, if you want to know what CPU you have on your computer, this is the Linux command for it. Again, as I told you, you can run Linux commands using the exclamation. Cat basically means to print something in Linux. Proc CPU info basically gives you the CPU info. Right, so it tells that this box or this collab is running on an Intel Xeon processor at 2.3 gigahertz and a bunch of information related to it. If you want to, sometimes this is useful when you want to decide whether you want to write parallel code or things like that, right? If time permits, we'll do one session on parallel code. If time doesn't permit, we'll do it as part of our weekly live sessions. Okay, cool. So next thing is, okay, if my number of jobs is large, because Xeon processors typically have 12 cores or 8 cores, they're fairly powerful computers. Again, not much, it's just roughly 14 seconds. Now, after all that, I want to plot this, right? Again, this is the same function that we used earlier. For PCA, we used this function, right? If you recall, I explained this function, plot embedding function with X and Y. We have seen this for the PCA example just above. Same function I'm using here. And again, I've just written the function again for clarity. When I embed it, this is the embedding I get. Now, the conclusions are important, right? First and foremost, this plot is better than PCA. So t-SNE plot in 2D is certainly better than PCA. Why am I saying it's better than PCA? Look at this. All the reds are again, this cluster is reds. This cluster is all blues. At least the similar looking person's faces are getting reasonably well clustered. Again, they're not perfectly separable. Again, remember, we are just doing in 2D, guys. We are taking a data which is 62,500 dimensions or fairly large dimensions, and we're trying to pose it into 2D, right? Again, look at this. All these points are well clustered. Again, there are some regions where everything is messed up. Look at this region. All the images are messed up here. Similarly, look at this region. There is a good amount of mess up here. Again, remember that t-SNE, PCA on real world datasets are never perfect. They're far from perfect, right? And if you notice here, this is a good cluster of red points. This is a good cluster of blue points. This is a good cluster of 0.4. This is better than PCA, but certainly not the best. Now, again, what I want you to try as part of the assignment is this. As we discussed in the course videos, I want you to try various perplexity values. How does this plot change if you use various perplexities? How does it change if you use different number of iterations? Now, a biggest question on your mind could be, okay, first and foremost, this is a summary, right? The t-SNE result is decent, better than PCA, but it is far from ideal. So first question that you should get in your mind is, why is t-SNE not working? Remember, the data that we have is fairly complex human faces. Image data is a fairly complex data. We humans have evolved for millions of years to recognize human faces. Let me give you a task, okay? Imagine if I show you 4 monkeys, different monkeys. Okay, I'll give you an example. Please bear with me. I've shown, let's say, 3 images of this monkey, 1. Okay, let's assume I have 4 monkeys, 5 images of this monkey, 2 images of this monkey, and 4 images of this monkey. Now I show you one more image. Can you tell me which monkey is this? Unless you are a biologist who works on monkeys, it's so hard. And what are we trying to do? What is t-SNE trying to do? t-SNE is saying, just given the images, it is trying to separate one image from other image by grouping them together. Right? Again, we humans cannot do it for non-human faces. Again, I've seen this happen to others also. People, like for example, I'm born in India. I can recognize Indian faces very well. Right? If you show me faces from a different country, completely different country or a different culture, where the faces, I've never seen such faces, let's say. For me, distinguishing one person from other person can be very difficult in the early days. Once I start working with them for a few years, once I start talking to them, or once I watch a few movies, it becomes easier. Right? Similarly, forget about humans. Right? If I give you other animal, if I give you dogs, okay, same breed, same everything, if I give you 4 different dogs, it's very hard to recognize. At least for me, it's very hard to recognize. Right? So please remember that image data is fairly complex data. And we humans have taken millions of years of evolution to recognize human faces. What t-SNE is doing is fairly good. Another very, very important thing here is we are ignoring all the spatial properties. Now, what do I mean by spatial properties here? Images have this property, very interesting property, which is given a pixel, all the pixels around it will be very similar to this, because pixels have smoothness, edges, all of these things. But what did we do? We took an image like this, we convert it into a one long vector, wherein we tick this row. This row is this row. Imagine that this is the image and I'm converting it to a vector. Okay. So this row is somewhere here. The next row is somewhere completely different. So the spatial coherence, which is very important for images, we have completely thrown it into the dustbin. We have not used any of that. Right? So later on, when we learn deep learning, we learn something called as a convolutional neural network, which is based on the convolution operator that we learned in linear algebra session. Right? So we just learned it, I think, in the previous session, right? So in the linear algebra session, we learned about the convolution operator. So there is a model called as convolution neural network that leverages this spatial coherence property, and it performs superbly better. Okay, just a simple mathematical transformation. So what we have done, again, there are 2 problems here. One, the way we represented the data is terrible. The way we represented the data is bad. t-SNE is not a magic bullet. It's not a magic silver bullet that will solve all the problems. So to solve this problem better, we'll learn in future sessions. Again, we have covered this in the course videos already. Hopefully we'll do this in the future sessions in this series. We'll learn how to use deep learning based convolution autoencoders, which is a very interesting idea which takes the ideas of convolution and a concept called as autoencoders, through which you can get very, very good representations that the visualization that you get at the end of it, is much better than this. You can do that. There are also other techniques like Siamese networks, FaceNet, etc., using which you can separate the face images much, much better. Right? So that's important. Okay, cool. So yeah, this is what I wanted to cover. I'll share this. Let me answer a few questions now. Okay. So somebody says, please give rough estimation of algorithms like logistic regression. I'll surely do that when we do the session on logistic regression. Today, I don't think we have time for it. So if the amount of information, so the next question is, if the amount, okay, let me just go here, right? Since anyway it is here. Okay. Again, folks, if you have not watched the course videos, you will see this as blunt stuff. Because you don't have the theoretical foundation, you'll not be able to understand it. Please understand that. Okay, all the people who think they're not understanding it because you have not watched the videos that I requested you to watch. Okay, so I can't help you with that. If the amount of information is equally divided amongst all the dimensions, right? That's a good question. In the real world on real data sets, this never happens. Of course, you can create synthetic data set where you can make this happen. In such a case, PCA is terrible choice, right? So, okay, somebody says, please conduct session on feature engineering. If time permits, we'll surely do that, right? So, what else? But within next 2 months, I know that I'll create a model to recognize them. I don't know what you mean, okay? Again, folks, please understand that if you're chatting amongst yourself, either you're not focusing on what is being covered, or you're not interested. In such a case, please don't join and waste others' time. But there are some students here who are answering others' questions. Thank you a lot. Great job, phenomenal job, because I can't answer every question, right? There are also some who don't go through the prior stuff or the prerequisites and come and they will not understand, obviously. Okay, cool. Do ML algorithms still used in real world problem? Yes. Who told you otherwise? I mean, I know personally algorithms that generate hundreds of millions of dollars, which just use basic classical machine learning algorithms. Because deep learning does not give additional lift on some data sets. Remember that deep learning does a very good job on images. It does a very good job on text. It does a very good job on speech. It does a very good job on audio. This is where it does terrific job. There is a lot of tabular data where handcrafted features are done, right? And in such cases, deep learning model versus, let's assume I use a GBDT, gradient boosted decision tree, right? So on this data set, my GBDT might perform very close to a deep learning model, right? Of course, in deep learning, let's assume I use a multi-layered perceptron, and let's assume the performance that I get from GBDT is very close to deep learning. What will I choose to productionize? I'll choose GBDT because it is computationally cheaper. It is computationally extremely cheaper than a complex multi-layered perceptron deep learning model. Again, this is the reality. So I know models in production today which generate hundreds of millions of dollars for some of the world's top companies that just use tree-based models or even logistic regression in some cases. So please don't fall into the trap that deep learning is everything. No, there are instances. Again, let's be honest here, deep learning has transformed a lot of these spaces. If your problem involves any of this, you should use deep learning. But if it doesn't involve this, make a sensible trade-off in terms of compute, in terms of training time and all of that, right? Okay, somebody says, are there better dimensionality reduction techniques? Yes, there are a ton of them. There are at least, again, I told you, right? Autoencoders is one way to do dimensionality reduction, right? So we have discussed that in the course videos also. There are tons of techniques, okay? I mean, I know at least 20 to 30 or at least 20 techniques I can quickly think at the top of my head. Again, some of them are not used extensively today, right? Again, depends on the context. PCA, TSNE are more widely used. Autoencoders is also widely used. Okay. So somebody says, okay, could you please explain the difference between sparse encoder and normal encoder? today I don't think the time permits. We have already overshot by 20 minutes, so I'll have to stop it. Okay, sounds good, folks. Unfortunately, I've overshot by a few minutes, but couldn't help it. So thank you very much, and hope I'll share this document with you. Hopefully, you will try more experiments as I've suggested. Hope this code walkthrough helps you and builds your skills on top of some of the theory and example code that we have covered in the course videos already. Okay, thank you very much. Bye-bye.